Welcome everyone to USB Forensics and Pen Testing at Pentester Academy. I'm Dr. Phil Polstra and I'll be your instructor for this course. And in this brief video, I'm going to give you a little bit of an overview of what's coming up with this course. So, where do we start? Well, some of you have probably seen me around. I'm a pretty frequent conference speaker. I've done some repeat performances at DEF CON. I've actually spoken at DEF CON 4 times in the last 3 years. I've spoken multiple times at Black Hat, GERCON, 44Con, some other conferences as well. Also been known to speak at conferences such as BrewCon, Sector, ShakaCon, and other interesting conferences that I discover along the way. Also an author, recently released a book called Hacking and Penetration Testing with Low-Power Devices. And this book is all about how you can build low-cost, battery-powered pen testing devices, drop boxes, remote hacking drones, etc., which you can operate in a big network, a big army of these things, from up to a mile or 1.6 kilometers away. My technical editor on that book needs no introduction. It's Mr. Vivek Ramachandran, who's the founder of SecurityTube and Pentester Academy. I'm sure you're all familiar with him. I also have 2 new books coming out this year in 2015. My day job, I'm an associate professor of digital forensics at Bloomsburg University of Pennsylvania. I've been programming since I was 8, programming in assembly since I was 10, and I've also been playing around with electronics and hacking hardware since I was 12. Also an aviator, been known to build planes and fly, teach people how to fly, work on planes. I have a dozen ratings for that sort of stuff. Without further ado, let's talk about this class. What's coming up? Well, we're going to start out by going over the USB basics. So we're going to have a good grounding in what's the hardware look like, what are the different versions of USB, how do connections work out, what are the standard device classes that are available for USB. We'll talk about endpoints and descriptors, all the details about USB and how it operates. We're going to focus a lot on mass storage devices. So we're going to talk about how do the communications work, what do they look like, what are the limitations for the NAND flash chips that are used in thumb drives. And we're going to spend a lot of time on that and how you can do fun things with USB. Well, what kind of fun things? We're going to talk about how you can make forensic duplicates of thumb drives using microcontrollers. So we're going to start out, and the first device that we're going to cover is this little guy here. This little guy is what I would claim is the world's smallest USB forensic duplicator. It fits in an Altoid gum tin, and it allows you to make forensic copies on the go of thumb drives. So we'll talk a little bit about how that works and have some fun with microcontrollers. From there, we will move up to a slightly more friendly microcontroller that has things like this. This has got an LCD screen. It has some buttons and such that allow you to do some more stuff. It's a little bit more user-friendly than the small version, which just has the blinky lights here. So we will talk about that. We'll get into microcontrollers and reading switches and outputting to screens as part of that process. We will move on to talk about USB write blocking. We'll talk about different ways that you can do that with software and, of course, with hardware. So we will talk about things like this little guy. This little guy is a USB write blocker that allows you to take a thumb drive, plug it in through this device, and block writes. And we'll talk about the details of that, and hopefully after you've gone through this course, you'll be able to understand how those things work and possibly make your own devices. Then the real fun starts. We'll get into USB impersonation. Why would you want to do something like this? Some people are using endpoint software that whitelists authorized devices. So we'll talk to you about how you can build something like this little guy here. This little guy here was presented at DEF CON a few years ago, and he allows you to plug your thumb drive into the device, and then your device will impersonate an authorized device. So we'll have some fun with that. And again, we'll have a little bit more fun with hardware and microcontrollers, buttons, LEDs, LCDs, etc. Along the way through this class, we're going to spend some time leveraging open source software, things like Wireshark. We'll show you how you can use Wireshark to sniff USB traffic. And we'll also cover some advanced topics such as dealing with Windows-only devices. And we'll also talk about things like UDEV rules that you can use in order to control how USB devices are treated on your Linux system and possibly in your VirtualBox hosted systems within that Linux system as well. So that is an overview of what we're going to talk about. I'm really excited about this course. And as always, if you're enjoying your time here at Pentester Academy, recommend us to a friend. The more people that we have subscribed, the more fun courses such as this one we can offer. I'll see you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing at Pentester Academy. In this video, we're going to cover some of the USB basics. We're going to start out with a really brief history. USB is something that's been around since the mid-90s. Before that, we had non-universal serial, we had PS2 ports, LPT or parallel ports, and life was really confusing. And so the guys got together, a whole bunch of people that is, and they decided to come up with something better. And they called it Universal Serial Bus, USB. And initially, we had just two speeds, low speed, 1.5 megabits per second, full speed at 12 megabits per second, and then with USB 2, we went up to 480 megabits per second, also known as high speed, and then with USB 3, up to 5 gigabits per second, that is, also known as super speed. So let's talk hardware. USB hardware is pretty simple. You have 4 wires, 2 power wires, 2 data wires, and it's set up so that you can't do something foolish. You can't do something that's going to blow something up or cause something not to work unless you make your own cables. It's also hot pluggable so that you can plug something in while the device is running and it should recognize it correctly. It uses differential voltages as opposed to some of the previous standards where you would have a high or a low voltage on a certain line. Here you have voltages that oppose each other. So you have a voltage difference between the two data wires that either increases or decreases. Also, it's something that allows you to have some pretty long cables, as much as 16 feet are possible. So for those of you that do metric, which is most of the world, that's around 5 meters or so. Okay, so what about the hardware? Well, the hardware has the 4 wires. I should point out that here I do not have the additional 4 wires required for USB 3 in order to do super speed. That, for our purposes, doesn't really matter because in terms of how the hardware works, it doesn't matter at all that it's USB 3 versus 2 or even 1. Over time, we've gotten to smaller and smaller connectors. We originally had the full size A connectors and B connectors, and then we went to the mini connectors, which are pretty popular on things like your Alpha wireless card, for example. And then we got into smaller connectors that you might find on things like your cell phone, the micro connectors. Great, so let's actually use this in Linux. So on the Linux platform, we want to have a listing of our USB devices. Well, how do we get that? It's pretty simple. The command that we use is just ls list USB. And that will give us a list of all the different USB devices on our system. Now, a couple things that you need to notice. This is for my laptop. My laptop has 2 USB 3 ports and 1 USB 2 port. Now, if you look at this listing, you'll notice that it seems to imply that I have 2 USB 2 ports and 1 3 port. That's not actually what's going on here. Here's what's happening. You need to have a USB 2 hub in order to support USB 2, and if your system supports USB 3, you'll need a hub for that as well. And what's happening here is my USB 2 hub, my USB 3 hub that has 2 ports on it also has to support USB 2. And that's why Linux sets up that second port. Okay, so notice that there are a couple of different devices. I have 3 buses in use here. Bus 1, bus 2, and bus 3. And it appears as most of my devices are in fact connected to bus 3. I have my Logitech device. We'll talk in future videos about determining what kind of device it is. This happens to be the headset that I'm using to record this video, and a few other devices. By the way, I can do an LSPCI and look to see what USB devices I have installed. And you'll notice that I have 2 controllers installed. One of them's a USB 3 controller and the other one is a USB 2 controller. So what happens if I plug in a hub? So I've plugged in a USB 4-point hub, and notice it shows up right here. And it shows up on bus 1. If I plug any devices downline on that hub, I plug something into that hub, such as a thumb drive, and I rerun LSUSB, now we see a new device, SanDisk Corp Cruiser Micro U3, right, on bus 1. Great. Well, what if I plug in a USB 3 device? So I've got a USB 3 device here. It's actually a software-defined radio. So if I plug that in, you might expect it to show up on my USB bus that supports USB 3. And sure enough, if I look on bus 2, I have a new device here. It says Open Moco Inc., which must be the manufacturer of the USB chip inside of the device. All right, so why am I making a big deal about the different buses? Here's the thing that matters to you. If you're going to investigate USB in further videos, we will talk about how you can use a tool such as Wireshark to sniff traffic. In order to sniff the traffic, you need to know which bus to sniff. If you sniff all of these buses, you're going to get overwhelmed with traffic, and you don't want that. Now, one thing you'll find out later is that if you take this bus, if you take a device that is supporting USB 3, it will be on an appropriate bus. USB 2 will be on an appropriate bus. If I plug a low speed or full speed device into any of these buses, it gets its own private bus. And the reason for that is those devices are slow, and nobody wants those devices bogging down their system. So in order to prevent that from happening, they give it its own bus, which might be desirable if you're trying to investigate a device. Now, you have to be careful, however, when you do this. If you knock something down to full speed, it might not behave exactly the same as it does at high speed or super speed. So that's something you'll have to keep in mind. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, tell a friend, and the more friends that you have that subscribe and join, the more awesome classes like this one we can provide. I'll see you next time. Hello everyone. Welcome to USB Forensics and Pen Testing at Pentester Academy. In this video, we're going to talk a little bit about USB connections. How are they established? So when you plug in a USB device, it's actually a 12-step process. So you connect the device, the hub detects it, the host, which is normally a personal computer, but it could be something else, is informed of this new device, and then the hub determines, is this a low speed or a full speed device? And it determines this based on the location of pull-up resistors on those 4 lines we talked about last time. It then resets the device, and it determines if it's capable of high speed using signals known as chirps. So it sends out chirps, and depending on the responses, it says, oh, you can do high speed. So why is it done that way? It's done that way for backward compatibility, of course. Because as you might remember, USB 2 introduced high speed. Once that's been established, they set up a signal path, and the host requests a descriptor in order to determine the maximum packet size. We'll talk more about descriptors in future videos. The host then assigns an address, learns what the device is capable of, loads a device driver, and selects a configuration. Now this is best learned by doing. So we'll go ahead and do a little bit of a demo here. Now last time we talked about using LSUSB as a way of seeing what USB devices are installed. So if I do an LSUSB, I will see several devices on bus 3 and nothing on bus 2 at the moment, which is my USB 3 hub, and a couple of devices on bus 1. If I take my thumb drive and I plug it in, I see that my thumb drive is going to show up, so I rerun LSUSB, and my thumb drive has showed up this time as device number 6 on bus 3. Great, so now what can I do? I can load a utility known as USB Mon, which is a module, and the way I load it is as root. I can use sudo if I wish. I do a mod probe USB Mon. And what this does is it creates several monitoring interfaces that I can use to intercept USB traffic. Now that I've done this, I'll go ahead and disconnect my device, remembering that it was bus 3 that was being used, and I will run Wireshark. And notice on my interfaces I have several available, including USB Mon 3 for bus 3. I'll go ahead and start a capture on this. And you'll see there's a whole bunch of traffic. Well, where's this traffic coming from? We talked about this before. We said sometimes you'll get lots of other traffic that you don't want. In this case, the traffic is coming from my headset that I'm using to record this video. Now, how could I isolate my thumb drive? I could kick it down to full speed and it would get its own bus. That's one option, but that again might change the behavior and how it acts. So you have to be careful about things like that. So for now, here's what I'm going to do. I'm going to go ahead and stop this, restart it, and then immediately plug in my drive. So restart, continue without saving. Boom, plug in my drive, let it capture for a few seconds, and stop it. All right, now if I scroll down to the end, I will very quickly see what address has been assigned to this device. I can also use LS-USB, and I see that it's been assigned device address 7. Great. So if I go back to Wireshark, where is device 7? There it is. There's a couple of things here. Now, the easiest way to filter out everything else, there's actually not a really easy way to filter out everything, because just like when you're doing wireless, the problem that you run into is that you want to only talk about traffic for this device, but initially it has no address. So you can't just say set the address equal to 7. But what you can do is say, let's let the address not be 3, 2. We don't want to exclude 1 because that would exclude our hub. But we can say 3 and 2. And that will at least get rid of some of the traffic, such as from my microphone. All right, so let's go back to Wireshark. And I will say USB device address not equal to 3 and USB device address not equal to 2. All right, and now I've cut down quite a bit. So how can I find my thumb drive connection? Well, what I want to do is I want to scroll down here and find the first place that the address of 7 has been used. Now I could use a search to do that. It might be easiest just to scroll like this. All right, so here we have it right here. Here's where it's got an address of 7. So what's happening? Here we have an unknown device that's been connected. So it's been connected. Here, initially, it's been asked, hey, tell me about yourself. Tell me about your device through something called a descriptor. And then it's been asked the question, which here's the response for that. And it says, tell me a little bit more about yourself. now that you've been connected. Actually, this one is for another device. I misspoke there. And here's the response. All right, so it responds and it says, here's a little bit about me. And notice that it says, I'm a Cruiser micro flash drive from SanDisk Corp. We'll talk more about those later. And then the host says, please set your address. It says, please set your address to 7. And it responds back and says, sure, no problem. Once that's been done, then the device says, describe yourself a little bit better to me. Here's the response. And it says, please, let's get this configuration. Again, that's one of the last steps to select a configuration. That's done here. And then we request some more information. We'll drill down into this in future videos. But you see, there's quite a bit that's actually happening here when the device is connected. Now, in order to understand some of these later things, that's the subject of a future video where we'll drill down into what are these things called descriptors and endpoints and how do those all work in the world of USB. So that's all for this video. As always, if you're enjoying your time here at Pentester Academy, feel free to recommend us to your friends in InfoSec. The more people that we have subscribed, of course, the more courses like this we can offer. I'll see you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing at Pentester Academy. In this video, we're going to focus on USB descriptors. So USB descriptors are very essential in your understanding of USB. So what are they? Well, they describe things, not surprisingly. They also have a standard format. The first byte in any descriptor tells you how long the descriptor is. You need to know such things so that you can say, oh, well, if the descriptor is only so long, then I know when I can stop reading the descriptor. The second byte tells you what kind of descriptor it is. And the rest of that is the descriptor itself. So the second byte has the type. Some of the most common types of descriptors that you will find are device descriptors. They tell you basic stuff about the device. And then there are configuration descriptors. And they tell you things such as how much power do you need? How many interfaces are there? So you're saying interfaces, what are those? Well, those are described in interface descriptors. So we'll talk in more detail in this video and also in the next about descriptors and interface descriptors and endpoint descriptors. Endpoints are virtual pipes that are used in order to send information back and forth between USB devices. We'll talk about those in detail as well. And then we have string descriptors. String descriptors are just strings. They tell you what something is called, what it's named. So what do these look like? Well, if we start with the device descriptor, again, all of them start with the length and then the type. And a device descriptor is type 1. So this is the very first descriptor that's read when a device is connected. After the type, it will tell you what version of USB it supports. Normally, you'll see USB 2.0, which is hex 200 in binary coded decimal. And then after that, you will see something called a class. Now, we haven't talked about classes except at a high level so far. We will definitely dive down deeper into those as well. in the future. I know I seem to be saying this a lot, and I apologize for that, but USB is a very big topic, and there's a whole bunch of information you have to understand in order to kind of get it at all. So we're kind of slogging our way through this. Now, the device class says what kind of device is it? Is it a mass storage device? Is it a human interface device, a keyboard or a mouse? Is it a headset like what I'm using now? There are different kinds of device classes out there. So the items that you see here in red are items that are particularly important to us if we're doing USB forensics, in particular if we're using mass storage devices. So in addition to the device class, we have a subclass and a protocol. Then we have the maximum packet size, and then we have a vendor ID. Every vendor who wants to produce a USB device is supposed to, in theory, pay money to the USB people to get their own vendor ID. Once you've done that, once you've spent the money, you're allowed to assign your own product IDs. And you can also give it a release number. After that information, you'll find other information that's not really necessary in order for the device to work correctly. A string for the manufacturer, and what's actually going to be there is an index that describes which string descriptor you have to retrieve to get the manufacturer, and the same thing for the product and serial number. And then finally, you have the number of configurations. Many devices support more than one configuration, and this will tell you which those are. All right, so what comes after that? After that, we have our configuration descriptor. We've determined what kind of device we have. We've determined its max packet size. And now it's time to look and see what is its possible configuration. What's the default configuration? And again, there could be more than one. Starts out the same. Length, descriptor type, and then we have our total length. And you might say, well, what's that all about? The configuration descriptor, you can think of this sort of like a header. It tells you about your device at a high level, and underneath the configuration, underneath this header, if you will, you'll have several possible interfaces. And because you might have more than one interface and you don't know how long all of this descripting information is for the configuration, you have to know the total length. And that's why it's repeated there. Number of interfaces, which configuration number this descriptor describes, and also an index into a string descriptor that has a nice human readable name for it. Then you have some attributes, and again, in red, because it's important, you have the maximum power. What's the maximum power that this device requires? Now, why is that important? It's important because if you ask for too much power, by the way, how much is too much? Most ports can provide 500 milliamps of power max. If you start hooking up hubs that aren't powered, you're going to have less power than that. So normally anything above 500 milliamps is risky to ask for. And we'll talk more about that in later videos. All right, so our next descriptor is the interface. How do I talk to this device? Again, starts out the same with the length, a descriptor type, the number of interface that this one represents, and how many endpoints, how many of those pipelines that it requires. Notice that once again we have the class, subclass, and protocol repeated. Why is that? Well, the reason for that is many devices are what we call composite devices. They support more than one device class. A good example, a camera. You have a camera, it can operate as a camera. It can also operate as a mass storage device. The same thing is true for many other devices, such as your cell phone. Your BeagleBone Black will present itself as a mass storage device, allow you to transfer files and such. So for various reasons, you might have more than one type of device available. So in order to support this, that information is repeated in an interface descriptor. Now, you might say, well, then how do you know what's up? We'll see later the details, but if you look into the configuration descriptor, it will say this is 0. This is undefined. It'll be defined later. Moving along. Endpoints. Those pipelines, they're described. We'll go over these details in more depth in a future video. But here we have things such as the address and the kind of endpoint that it is, its maximum size, that sort of information. Finally, we have string descriptors. String descriptors are used to present strings. So we have indexes for these strings and many of the other descriptors, and then we have the strings themselves in Unicode. Now there's a note here. There's a special case. If you have string 0, if you ask for string descriptor 0, that should return a list of available languages. The most common is hex 0409, which stands for US English. By the way, interestingly enough, I found that most devices return US English even if they were made in the UK set, which I find kind of interesting. All right, so let's bring this together, and then we will pause, and in the next video we'll go through a demo of this. But recall from a previous video we talked about USB connections, and we said here are the 12 steps that happen when you connect a device. Now, where I've bolded is where descriptors come into play. So notice the very first place is the host requests a descriptor for the device. So it wants to know that maximum packet size. Then it assigns an address, and then it learns its device capabilities. How does it do that? It asks for the configuration descriptors, the interface descriptors, etc. And then it selects a configuration. It says, among the choices you gave me, this is the one that I want. That's all for this video. As always, if you're enjoying your time here at Pentester Academy, recommend us to your friends so that we can provide you more good, exciting quality videos. See you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to pick up where we left off in our last video. We're going to talk a little bit about USB descriptors and how they work in detail, and we're actually going to go through a little demo. Now, before we get started with that, I just wanted to very quickly bring back this USB connection slide and remind you of the 12 steps. Here are the 12 steps, what happens when you connect a device. And the places that are bolded, such as here, where you're requesting a device descriptor in order to get the packet size, and then here where you're learning capabilities by requesting configuration descriptors, etc., and then finally selecting a configuration. All of those involve descriptors. So let's go ahead and run through a demo. All right, so I'm going to go ahead and load USB mon. We learned about that before. So mod probe USB mon. And that should allow me to go ahead and monitor my different interfaces. All right, so I'm going to take a little basic thumb drive here again, and I'm going to plug it in. And first I'm going to do an ls USB. And I see my 3 buses, as I've seen before. I plug in my device, run ls USB again, and I should see my trusty SanDisk Cruiser micro flash device. Great. And it is listed as being on bus number 1, looks like today. So I'll go ahead and fire up Wireshark. A little warning there. USB mon 1 and start. And here I get a whole bunch of information that's coming through. And I will unplug my device. I will stop my capture and I'll restart it. And I'll once again plug in my thumb drive. It appears as though it's been assigned address 4. I'll stop this. And now let's have a look at those descriptors. All right. So once again, I'm going to use LSUSB. And what I'm trying to do here is I'm trying to eliminate other devices. So I have a device 2 as well. And then I have device 1, which is the root hub. We'll talk more about what a root hub means in the future. I know I say that a lot, and I apologize, but that's just kind of the way it is with some of these things. So I'm going to go here in Wireshark, and I'm going to say USB device address not equal to 2. And then I'll scroll down to where I plugged in my device. Here we are. And the port was reset. It was cleared out. And here I'm asked device 0, because I don't have an address yet, please give me your device descriptor. And my device responds and says, this is me. I am a device descriptor. Again, length, type, USB 2. My device class is 0. We said in the last video that the device class of 0 means I will tell you later what I am. Same thing with subclass and protocol. And my maximum packet size, by the way, is 64. My vendor is SanDisk. This is the ID assigned to them. And here's the product ID, which Wireshark is nice enough to decode for me. And here are the indexes into the string descriptors for manufacturer, product, and serial number. this device supports one configuration. Great, so now the host knows how to talk to this device, and it says, please reset and now once I've assigned an address of 4 to my device, the host says, destination 4, please give me your device descriptor. And you might think, well, that's really strange. Why is it asking for that again? Well, that's just the way it works. So we have the same device descriptor repeated, and now it says, give me your configuration, give me that header information. And here is my response. I am not self-powered, I don't have remote wake up, and I need at most 200 milliamps. If you expand this in Wireshark, you'll see the different bit fields being set. Hex 80 is what you have. So now it knows how much power is required, and it needs to get some more information. So it says, get that descriptor again. You're thinking, what? Wait a second. I just got that descriptor. What's up with this? Remember from our previous discussion that here we have the total length for this descriptor. Remember, the configuration descriptor you can think of as a header. It tells you at a high level about the device, the different configurations it has. So in one particular configuration, it might need a certain amount of power. It might have another low power state. That could be a different configuration. You don't know how much configuration information there is there. In this case, there's 32 bytes. So you have to ask again, because now you know that there's possibly more to the story. So here I ask again, and that's sent. It's sent again. And once that's been sent, it asks for strings. It says, give me one of those strings. Well, which string is it? I would like string index 0. We said last time, what is index 0? That is a language descriptor. What do you think it's going to reply with? Well, it's going to come back and it's going to say, well, thanks for asking. I am, in fact, supporting United States English, hex 0409. So let's walk through this really quickly again. The device was asked for its device descriptor in order to get the max packet size. Then it was assigned an address. Then it was asked for that descriptor again. Then it was asked for the configuration descriptor in order to know things like how much power was required and how long the configuration information was. It then asked for that information again so that it could get the whole story. After requesting that for the second time, now the host is asking for certain things such as, what language do you support? And now it wants another string. In this case, it says, I want string 2. String 2 is the manufacturer, Cruiser Micro. Excuse me, actually it's product ID in this case. I'm going to ask for another string, this time string 3. String 3 is the manufacturer, SanDisk Corporation. I'm going to ask for yet another string, string 3. Not sure why they would ask for that again. Oh, I think I might have made a mistake. I must have had my index wrong, and now it's getting the serial number, which is what this is right here. By the way, all mass storage devices are supposed to have a unique serial number. All right, finally, I can set the configuration. I can say, which configuration do I want? Well, there's only one possibility for this device, configuration 1. So now the host says, please, can I use configuration 1? And I get a response, and then more configuration occurs from there. And the stuff that happens after this point is actually specific to USB mass storage devices. And that's all we have time for in this video. As always, if you're enjoying these videos and all the videos at Pentester Academy, tell a friend. Help us to make more and more of these awesome videos for you. See you next time. Hello everyone. Welcome to USB Forensics and Pen Testing here at the Pentester Academy. In this video, we're going to talk a little bit about endpoints. Now, what's an endpoint? An endpoint is a virtual wire, if you will, a virtual circuit. It's a unidirectional pipe that's used to send data to and from your USB devices. Now, the direction for these, by the way, is relative to the host. So it might seem a little backwards at first. If you're thinking about the devices themselves, you might think, well, I'm going out of the device. Well, it's into the host. So that sometimes can cause confusion when you're starting out. Other nice things about endpoints that you should know. If there's any packet fragmentation and handshaking, all that stuff is normally done by the hardware. So if you're doing some work with USB, you normally don't have to worry about that. Now the high bit of each endpoint address tells you which direction the data is going, if it's an in or an out endpoint. And there are 4 different kinds of endpoints. We have what we call control endpoints, bulk transport, interrupt, and asynchronous. So what are these all about? Well, let's start with control endpoints. Every device has to have a control endpoint. It's the primary mechanism for most devices to communicate with the host. There are some exceptions to that. We'll find out later that the USB mass storage devices are an exception to this rule. And every device must have at least one control endpoint. Normally we call it EP0. I incidentally have never seen a device that had more than one controlled endpoint, but it is allowed. And this endpoint allows the device to respond to standard requests such as get and set your address, have some descriptors, have power and status information, and it might also respond to some other commands, and we'll talk about that in a later video. Now, the control endpoints have up to 3 stages. There's a setup stage, and in the setup stage, there's a token that's sent in order to say, hey, there's a setup request coming along, and if the device receives it, it is acknowledged, and the setup request is sent. It's 8 bytes long, and the first byte is a bitmap that tells what sort of request it is, and the rest of it are parameters for the request. Then there's an optional data stage. Some requests return data, some of them don't. And then there is a status stage where a zero-length packet is sent as an ACK if everything worked. Interrupt endpoints. Interrupt endpoints are used for slow devices such as keyboards, where you don't want to pull all the time and do busy waiting. Normally, These are low-speed devices. This allows you to have longer cables and such. Asynchronous endpoints are used where you need guaranteed bandwidth. Let's say you have some streaming video, or maybe you have audio, such as the audio for my headset that I'm wearing right now. And it's used primarily for time-critical applications. And that brings us to bulk endpoints. Now, bulk endpoints are what you're going to use extensively with things like mass storage devices. Some people actually refer to them as bulk-only mass storage devices. The thing about bulk endpoints, there's no latency guarantee. So if you're trying to stream media, it's not the one that you want to use. However, if you have an idle bus, if it's the only person on the bus, the only device on that bus, it's going to give you good performance. If there are other kinds of traffic, it is superseded by everything else. So that's why you want an idle bus to use it. For full speed and high speed, you have 8 to 64 byte packets for full speed, that is. And high speed only allows 512 byte packets. If you have a high speed bus, you don't want to tie it up with all these little teeny tiny packets. Now, in bulk endpoints, they have transactions where you have a token that's sent, and then you have your data packet sent, and then there's an ACK handshake that's sent if this all succeeds. Great. Well, let's actually look at this and how it works. So let's do a little bit of a demo. So here we are at our command prompt. Hopefully by now you remember how this works. I'm going to go ahead and do a mod probe, USB mon, and I'll go ahead and run Wireshark. Get my handy dandy USB drive, plug it in, and now I'll run my ls USB, and I see that once again this has come up on bus 1. So that is the bus that I want to capture on. I'll go ahead and unplug here, and let me bring up Wireshark on the screen that I'm actually recording. All right, so I'm going to go ahead and start my capture on USB 1. Start my capture, and I'm going to be ready here. I'm going to plug in my drive, and then I'm going to go ahead and stop it. Okay, so let's see all of those different endpoints. Let's see, how can I tell which endpoints are being used? I'm going to go ahead and say USB device address equals 5. Oops, that should be equals 5. And of course, this is going to eliminate those set address, etc. commands. But I just wanted to show you how you can tell which endpoint is being used in these transmissions. So here, the host is saying to the source, to the device, please give me your device descriptor. So here, under USB URB, you'll notice that it says my transfer type is control. And it's an in endpoint, which makes sense. information is going in to the host. All right. And as expected, my response is also a control endpoint going in. Then I request my configuration. I get the response, all of this on control endpoints. Then I request it again. We talked about this in a previous video, how it's requested and then it's requested again because there is information, there is a length, the total length that has to be sent in my response. So I respond back, and in my response back, I say, here's my configuration descriptor. Now, thankfully, Wireshark will go ahead and decode all of this for you. So my total length is 32 bytes. It will respond back, and then it's going to ask for some string descriptors. Again, all of this occurs on the control endpoint. Control endpoint is pretty much used for standard commands that every device must support. All right, so we see some other requests, and now we see things like give me the max LUN. We'll talk about what that means later. And all of this is still occurring on the control endpoint. And then finally here, you'll notice that there is a bulk out. There's a request. And this is a bulk out endpoint. And immediately following, we have traffic on a bulk in endpoint. And then you'll notice as soon as we start having the USB mass storage protocol here, all of the traffic from this point on, for the most part, will be on those bulk endpoints. And we'll talk about that when we go into mass storage devices in detail. Incidentally, really quickly, this just show you a different kind of traffic. If I do an LS USB, you will see that on bus 3, I have my Logitech device, which is my headset. So if I go back to Wireshark and I start a new capture, and this time I'll start my capture on USB 3 without saving. Oh, I'm not getting much because I didn't clear this expression. There we go. I'll just go ahead and stop that. And notice it tells me right here that this is asynchronous endpoint traffic. Well, that's all for this video. As always, if you're enjoying videos such as this at Pentester Academy, tell a friend and help us get more subscribers. More subscribers means more videos for all of us. See you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing at Pentester Academy. In this video, we are going to have a look at USB basics. We're going to look at some device classes and also commands. And we're getting close to the end of the basic module. So you might have heard me say several times, in a future video, we'll talk about this. In a future video, we'll talk about this. So hopefully that will come to an end soon. So let's start with device classes. Well, what are they? A device class is something that answers the question, what kind of device is this? there are a lot of device classes out there. If you go to usb.org, you can get a complete list. Some of the more common ones that you'll see: HIDs or HIDs, human interface devices, such as a keyboard or a mouse or a joystick. Audio devices, such as speakers, microphones, etc. Printers, mass storage devices, something that we're going to focus on a lot. Now, all these devices have to be able to respond to certain commands. Now, there's what we call standard commands, and a standard command is something that all devices must respond to. Sometimes these are called requests, if you look at the USB specs. And these include things such as get and set your address, get your status, are you even there? Get or set a descriptor, clear or set a feature, or get or set a configuration. And then we have class commands. So every class defines commands that are specific to that kind of a device. So, for example, it wouldn't make sense to tell a printer to please stream an audio file or a video file. One thing that is nice about device classes is this allows all devices of a certain type to be treated the same, and it shifts the development of drivers away from the manufacturer and toward OS people. So when I plug in my thumb drive, it works the same as every other thumb drive. And each manufacturer doesn't have to make their own. Now, if there is a case where someone wants to make their own, they can use vendor-specific commands, and those are permitted in the standard. So we saw before that each device has a vendor ID and a product ID and possibly a serial number. And there is the ability to extend commands and have some extra functionality with vendor-specific commands. This is not very common, however. I haven't really seen a lot of this being used. Okay, so let's have a look at device classes. So we'll go ahead and fire up our terminal. And once we've done that, we will go ahead and run mod probe USB mon. Should be used to this by now. So mod probe USB mon. And now we'll go ahead and run Wireshark. All right, great. So we're running Wireshark. Let's start with my trusty thumb drive. Let's plug this in and we'll see what it has to say. So we'll plug it in and we'll use LSUSB to verify. Should be on bus 1, and it is. By the way, these buses, in the case of high-speed devices, are determined by the port. So if you plug things into the same port over and over again, in theory, you should get the same bus, at least on your Linux system. But of course, who's running anything else? All right, so I'll go ahead and start a capture on this. I will plug in my device, and I'll go ahead and stop my capture. All right, so we'll use this for now. We'll say USB device address equals 7. So it looks like that starts at around packet 97. And I'll go ahead and clear that. And I can see what came right before it. And I see right before this, there was device 0. Again, that's usually the device number that you're going to have for a brand new device. It asked for the device descriptor. This is that first ask. And then a little bit later, here, that same device is asked for its device descriptor again. So what's in this response? Once again, Wireshark is nice enough to decode this for us. So I can see that here's my vendor ID, which Wireshark has decoded, my product ID, my device, and my manufacturer. Again, this is an index into the string descriptor for my manufacturer. So let's look at this command. So here's my command, and I sent a request called get descriptor, which is request 6. I can see that right here in my packet dump. And index is 0, descriptor type is 1. Right? So I'm asking for a device descriptor. Then I'm going to ask for a configuration descriptor. Again, I'm going to do a get descriptor, command 6. In this case, I'm asking for index 0, the first configuration, and it's type 2, which is a configuration descriptor. So here we see the responses. All right, so let's back up for a second here. Let's look at that device response. Notice that the class was 0, and the subclass was 0, and the protocol was 0. And it says here on my Wireshark window that it's going to use the class code info from the interface descriptors. All right, so we had asked for the device, we asked for the configuration twice, we asked for some strings. Incidentally, Linux and Windows treat these differently. So you should be aware that something slightly different will happen with Windows. In general, what you'll find when it comes to mass storage devices is that Windows will pull in less information originally than Linux will. All right, so now we've gotten all of our information. And here I have my interface descriptors. All right, and it says, what's the class? The class is mass storage. Class 8. Again, here it is. How many endpoints does it have? It has 2. Right. And what's the subclass and what's the protocol? This is the most common subclass and protocol that you'll find. We'll talk more about that in our discussions of mass storage devices. And then we have our endpoint descriptors. Now remember that we said previously that the mass storage devices, or all of the devices really, the configuration descriptor is a header, and on the first request, and then the next request gives you everything else. It gives you the interfaces and it gives you the endpoints. So there are two endpoints. So there's one endpoint descriptor for a bulk in and another one for a bulk out. Well, that's all for this video. As always, if you're enjoying your time here at Pentester Academy, tell a friend. Help us spread the word. See you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing at Pentester Academy. In this video, I'm going to give you guys your first challenge. So we finally learned enough about USB. It's a big topic, but we've learned enough about all the different pieces to try to put it together. So here's what the challenge is. I've created a few capture files for you to look at. So those are attached to this video. And for each of those, your goal, your challenge is to determine what kind of devices are being sniffed, who made it, etc. And I will warn you that some of these devices will be composite devices. In other words, devices that have multiple device classes in a single physical device. So they're going to have more than one configuration possibly, and more than one interface as well. And here's what I want you to find out. I want you to find out for each of these, who made it, what's the name of the manufacturer and the product name. Also, what is the vendor ID and product ID? These aren't necessarily going to be the same thing. The first two items are strings, the next two items are ID numbers. How many configurations are in each device? And for each configuration, how many interfaces and the maximum power permitted for the device in that configuration? And for each interface underneath that configuration, what is the class, subclass, and protocol for the device? How many endpoints does it have? And for each of those endpoints, what is their address, what is their type, and what is their direction? All right, that's all for this video. We'll have answers in the next one. And as always, if you're enjoying your time at Pentester Academy, recommend us to a friend. See you then. Welcome back to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to give you some answers to the challenge from the last video. Hopefully you were able to get all of the requested information yourself. And just as a reminder, what was the challenge about? The challenge was to examine some capture files and determine what sort of devices were being sniffed. And in particular, I gave you a list of details for each device. Let's go ahead and use Wireshark to find the answers. By the way, if you just want to check your answers, you can also look at a partial answer is in the USB challenge spreadsheet, where I've gone through each of the 5 devices and laid out the different information. So that is available for download as well. All right, so let's do it the fun way. Let's have a look at Wireshark. So looking at Wireshark, this is the first file. You'll see there's a bunch of traffic, and then my device is connected. And as soon as the device is connected, it gets a descriptor. And the device descriptor says that this is a vendor ID of OpenMoco Inc., product unknown, and more information is, of course, in the string descriptors that come later. All right, so once that's done, you'll notice that we get a configuration descriptor request. We get the first request, which is short. Remember, why is it short? Because of this. It has to find out how much information is in the entire descriptor. So it asks for it again, and this time around, it gets everything. So what does this tell you? This tells you that this device has a maximum power requirement of 200 milliamps, and it has one interface, and this is configuration 0, the only configuration. So if we look at interface 1, or the first interface, which is normally interface 00, here's what we're going to see. It's an interface, and it's a vendor-specific class, hex FF or 255. Now, one thing that's unique about this device, those of you who went through this exercise may have noticed this, is that we have a lot of alternate settings. So here's one setting, which has no endpoints, and then here's an alternate setting. And this alternate setting, 0.1, has 4 endpoints. So if we look at these 4 endpoints, we will see that we have the first endpoint is an in endpoint, and it's a bulk endpoint, and it has an address of 1 with a maximum packet size of 1024. After this, we have this unknown descriptor, and if you look at this, you'll see that it says SuperSpeed USB Endpoint Companion. This just means that Wireshark doesn't know how to interpret this fully. However, this is a SuperSpeed endpoint, so this is a USB 3 device. The next endpoint, very similar, except for it is an out endpoint. Once again, it is a bulk endpoint, and it has the same endpoint number of 1, which is allowed if you have different kinds of endpoints, either different types or different directions. They are allowed to duplicate the endpoint number, which some manufacturers do this and some of them do not. So this is something you'll notice as you examine USB devices. Again, there is SuperSpeed. The third endpoint, endpoint 2, is a bulk in. SuperSpeed endpoint, and there's another bulk out. And then there's yet another alternative for interface 0. I won't go through all this. And there's another one, 0.3. So this device is a little bit strange. All right, so what is it? Some of you might have your suspicions already. Well, definitely you should know what they are if you did the exercise. But if we look at our string descriptors, the first one is going to be what kind of language do you speak, and everyone speaks US English. And what is the product? This is a Blade RF, and it's made by Nuand. So as you may have suspected when you started looking at this, this is in fact a software-defined radio, a Blade RF device. All right, let's move on to device 2. Device 2, here's our capture. We see here that it's been assigned address of 10. And this is reporting itself as being from Toshiba America and an unknown product with one configuration. So then we have our configuration request response. And notice that this claims that it only needs 2 milliamps of power, which I suspect is not actually the case. We'll talk more about that later. I know I've said that we would stop saying that all the time, but we'll say it less and less as we go on. All right, so here I've gotten my descriptor, my configuration descriptor, the whole thing. This one's a little bit shorter. And how many interfaces do I have? Just the one. And this, again, is telling me that it needs only 2 milliamps of power. However, if I drill down into the interface, it tells me this is a mass storage device, subclass 6, protocol hex 50, and it has 2 endpoints. And if I look at my endpoints, here's endpoint 1, which is a bulk. It says bulk in endpoint with address 1 with a 512 byte packet size. And as you might expect, there's a bulk out endpoint also with 512 byte packet size. So this is actually an external drive. We can get more information when the string descriptors are retrieved. And it says external USB hard disk drive, which is what it is. And it's made by Toshiba. Great. Let's look at the next one. So if I look at device 3, see device 3 is getting assigned an address of 12. Here's my response. It says my vendor ID is Logitech. The product ID is unknown to Wireshark. And there is one configuration. And here I'm getting some device qualifier requests that are not being processed very happily. That's not something to really worry about. And notice here it says that my maximum power is 100 milliamps. And I'm going to request the configuration. Here's the big request for the second time. And how many interfaces does this have? This has 4. All right, so here's my first one. And notice that it says it is a class audio with a subclass of 1. There are a bunch of unknown descriptors, audio control interface descriptors. Don't concern yourself with those. And then we have this. This had no endpoints. Our second interface also has no endpoints, and it's an audio device subclass 2. Now, what you'll notice is that there are alternative interface settings. So here we have alternate 1.1, and the alternate has an endpoint. What kind of endpoint? It has an asynchronous in endpoint. And then if I look at the next interface, the third one, 2, once again, it's an audio interface with a subtype. And here you'll notice that it has no endpoints, but the alternate setting has 1 endpoint. Well, what about that endpoint? That's an out endpoint. And it's also asynchronous with a weird maximum packet size. All right. And then we get to something rather interesting. We get to a HID device. Now, this is definitely a very composite device. There's lots of different kinds of things going on here. Here we have a HID device. It has a interrupt in endpoint with an address of 4. So what is this thing? Well, if you look a little further into your trace, you'll notice it says Logitech USB headset H540, which is the headset I'm wearing right now. So all of these different types of devices wrapped up into this one physical device are performing different functions. So there is a device or an interface for the microphone. There is a device and interface for each of the speakers in the stereo headset. And there is a device for the controls. So I have some buttons on this headset to mute the head microphone and also to adjust the volume. So all of those things are in this one big device. So here you've got everything wrapped up together. All right, moving on. Let's look at device 4. Device 4 was assigned an address of 13, and it says it's a Realtek Semiconductor Corp RTL8187 wireless adapter. And then we request our configuration twice. The second time, we see that there's one interface, and this requires up to 500 milliamps of power, so up to half an amp, which is quite a lot, typically the maximum that you can have for a USB 2 device. And it has a device class of nothing, and subclass of nothing, and protocol of nothing. So it's somewhat interesting that you have this. Now this is 00, the interface descriptor. It has 3 endpoints. There's a bulk in with address 1, max packet 512. There's a bulk out with address 2, also with 512 bytes maximum size. And then here we have another bulk out with the same packet size. So this one is a little bit peculiar. Now if I look at the strings, I will see that this is a product RTL8187 wireless, and the manufacturer is listed as Realtek RTL8187. In reality, as some of you may have expected, this is actually an Alpha wireless card. All right, let's have a look at the last device. So our last device was given address 14. It has an interesting case, has one configuration, and this is a miscellaneous class device, subclass 2, protocol 1. The vendor ID, Linux Foundation, and the product ID is multifunction composite gadget. I wonder what this could be. So here once again we have our 2 configuration descriptor requests, and this guy's got 5 interfaces, so he's got quite a bit. Looking at the first interface, it says class communications and CDC control. This interface has one endpoint. If you look at that endpoint, you'll see it's an interrupt in endpoint with an address of 2. If you look at the next interface, it has a class of CDC data, and it also has a couple of endpoints, in this case 2. There's a bulk in endpoint with an address of 1 and a bulk out endpoint with an address of 1 as well, with 512 byte packets. The next interface is a communications and CDC control interface with an abstract control model subclass and AT commands for its protocol, which sounds a lot like using a modem. Some of us might remember using those things. All right, endpoints. How many endpoints? Just the one. Here's the endpoint. It's an interrupt in endpoint with address 4. Another interface. This one also class CDC data. So we have CDC data. Has 2 endpoints. Not surprisingly, bulk in. This one with endpoint address 3. And this one bulk out with address 2. And then finally we get to a class of mass storage, subclass 6, protocol hex 50. And this has 2 endpoints, a bulk in endpoint with address 5 and a bulk out endpoint with address 3. Wow, there's a lot of stuff there. I wonder what this could be. Well, here again, we have our first string descriptor request, and the next one says this is in fact a BeagleBone Black, which is made by Circuit Co. Now, one thing you should realize, the manufacturer string is not always going to be correct. We saw that with the Alpha card. It didn't say Alpha, it said Realtek. And this is another case of that. This is actually a element 14 BeagleBone Black that I used for this capture, but for compatibility reasons, it will show up as a Circuit Co. BeagleBone Black because they're identical. They're just made by different people. All right, well, hopefully you enjoyed this challenge. And remember, as always, if you're enjoying your time at Pentester Academy, recommend us to a friend. I'll see you next time. Hello, everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to talk a little bit about USB hosts and hubs. Let's start with the host. So every PC has at least one host controller. And what does this host controller do? Normally, it manages devices that are connected to the USB bus. So it manages the data that goes to and from that bus to the PC. And it also, in some cases, polls devices. We've seen interrupt-based endpoints that require us to poll devices. There are other cases where devices must be polled, and this is done by the host controller. Now, if it's a USB 2 chipset, it probably is using the Enhanced Host Controller Interface Standard, or EHCI, whereas if it is a USB 3 controller, it is probably using the Extensible Host Controller Interface known as XHCI. So how do you find these host controllers on your PC? Well, it's pretty simple. If you do an LSPCI and possibly pipe that to grep USB, you will see these different controllers which are connected to the PCI bus. And it looks kind of like this. You have your controller, and in this diagram it shows you a UHCI controller, which is a USB 1.1 controller. And then you have your EHCI controller. and a port router. The port router is essentially a hub, and this is called a root hub. Now, one thing it's important to know is that in most cases, the lower speed traffic or the older standard traffic will be segregated from the more modern traffic. So here we have USB 2 traffic, and here we have USB 1 traffic and or low and full speed traffic being handled by a separate chip. It's important to realize this because if you have a lot of these lower standard devices connected to a more modern hub, such as a USB 3 hub, it can cause some bogging down and a bottleneck for those particular devices. And this is showing a USB 2 hub. So what do hubs do? Well, the hub's job is to monitor insertion removal of devices, manage power. Again, if it's a USB 2 device, you can get up to 500 milliamps. 500 megaamps would be way too much. 500 milliamps, and if it's USB 3, you can get up to 900 milliamps of power. Now, if it's directly connected to the host controller, as we said, it's a root hub. Now, if it's a USB 3 hub, a couple of things you should realize. A USB 3 hub actually contains an entire USB 2 hub. And why is that? Well, it's because that it works fundamentally differently from USB 2 in that it's actually a switch. Well, what does that mean? If you think to networking, when you buy a network switch, all the traffic for each port goes only to that port, not to everybody else. If you look at a USB 3 hub, it's the same situation. So if I connect a USB 3 device to a port, that port gets its own dedicated connection, just like switched Ethernet. And because of that, and because it works differently, you'll notice in some of the traces that we looked at previously, the USB 3 device didn't have get and set address commands being sent to it. And the reason for that is the only device on that bus. So there was no need for that. Also, if you have a USB 2 device, you don't want it bogging down your USB 3 devices. And here is a nice picture showing you what these all look like. Again, you have USB 3, super speed, USB 2, high speed that's separated from full low speed USB 2 or USB 1.1. It's important to note, even though it's not showing this way in this diagram, if you plug a USB 2 device into a USB 3 port, it's still going to be segregated like this. All right, now let's have a little bit of a demo. So we'll have a look at these things on my system here. So first I'm going to do an LSPCI. I'm going to pipe that to grep USB. And here you have my two controllers. Here's my XHCI controller, my USB 3 controller, and here is my USB 2 controller. If I do an LS USB, what will I find? I'm going to find a few devices on bus 3. So here on bus 3 I have several devices, including a thumb drive, a 4-port hub, an external hub, a PNY thumb drive, and a few other devices as well. What about bus 2? Bus 2 has the hub and my one SDR. That's the only other device on that bus. Even though this device here, this Logitech headset, is plugged into a USB 3 port. It's still been segregated. And in fact, it's connected to that root hub, the USB 2 root hub that is integrated inside of my USB 3 root hub physically in terms of what's in the devices. All right, incidentally, one of the other things you might find interesting, this PNY device is not a PNY device at all. In fact, this is a thumb drive that's been connected through the USB write blocker that we're going to show you how to build in some later videos. That's all for this video. As always, if you're enjoying these videos here at Pentester Academy, tell a friend and help us spread the word. I'll see you next time. Hello, everyone. Welcome to USB Forensics and Pentesting here at Pentester Academy. Today is a day that some of you have probably been waiting for. Why is that? Today we're going to start in on USB mass storage devices. So we've learned enough about USB in general and how it works so that now we can finally move on to our main topic for this course of mass storage devices. And we're going to start with a description of descriptors and endpoints that you will find in USB mass storage. All right, so what will you find in mass storage descriptors? A couple of things. The class for USB mass storage is 8. That's the class ID number. And the typical subclass number is 6. And what 6 means is that you're using bulk-only transport. Now, bulk-only transport means that all of the communications will be done on bulk endpoints. We'll talk more about those endpoints later. And then finally, the protocol is hex 50, which is the SCSI instruction set. Now, even when you have something that is just a flash drive, just a storage device and nothing else, for whatever reason, typically you will find the class, subclass, and protocol at the interface level, not at the device level. So if I grab, any old thumb drive such as this one, and I plug it in, I will find that it has the class, subclass, and protocol at the interface level. Another thing that's slightly different about the mass storage devices is that a serial number is required for a mass storage device. For many other kinds of devices, a serial number is optional, but not in this case. All right, so let's talk about endpoints. So we said that we're going to use only bulk endpoints. And given that, at least 2 of them are going to be required, one for in and one for out. Now, these endpoints must support full and high speed, and something you should be aware of, full speed might be far from optimal. What I mean by that is the device is required to support full speed operation, but not very well. It's sort of like in the aviation world, if you have an aircraft engine, by regulation, it has to operate with half of its maximum oil capacity, but it doesn't have to operate efficiently. The same thing is true here with our thumb drives. The max packet size is typically 64 bytes for full speed and 512 bytes for high speed. All right, so let's have a look at descriptors and endpoints. So let's do a little demo. We go ahead and bring up my terminal window here. And as we are used to doing by now, I'm going to go ahead and run mod probe USB mon, run Wireshark, go ahead and put my Wireshark over here, and now I'm going to plug in my drive. I'm just going to grab one from my pile here at random. I have a few of these, as you might imagine. Plug it in. And now I'm going to do an ls USB, figure out what bus was used, and sure enough, it was bus 3. So I'm going to go ahead and unplug and go back to Wireshark. And then we'll go to USB Mon 3, click Start, and plug in my device. And I see some traffic related to that device. I'm going to go ahead and stop. I see a lot of other traffic as well, which is something I probably didn't want. All right. If I go back to my terminal real quickly, do an ls USB, I will see that this is device 8. So if I go back to Wireshark, I'll say USB device address equals 8. And here we go. We can scroll to the very start. Notice that it is setting the address to 8. And as we're accustomed, it first asks for the device descriptor. And the device descriptor is here. It says SanDisk Corp, Cruiser Micro. Notice, as I said, that the class, etc. are all zeros. Then we request our configuration the first time, and it says 200 milliamps is max power for the device. And then here we ask for the full configuration descriptor. So we have one interface, and that one interface is here, and it defines 2 endpoints. It's mass storage with bulk only transport using the SCSI protocol. The first endpoint is an in endpoint, and it's a bulk in endpoint with a maximum packet size of 512. And the second endpoint is also a bulk endpoint, but this one is an out endpoint. And on this device, this has been designated endpoint 1, and this has been designated endpoint 2. As we said before, sometimes you'll have a manufacturer that will give them both the same number, which is allowed as long as they're a different kind of endpoint, although it can be a little bit confusing sometimes when you're dealing with them. Well, that's all for this video. As always, if you're enjoying your time here at Pentester Academy, tell a friend and help us spread the word. See you. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we are going to have a look at USB mass storage presentation. How does a USB mass storage device present itself to your computer? Now, nearly all flash drives present themselves as SCSI hard drives. And you might be thinking, well, it's not a SCSI hard drive. Well, it's not, but it looks that way to your computer. And typically these hard drives that they emulate have 512 2K or 4K byte sectors, although 512 is pretty much the industry standard. I haven't really seen any devices that have 2K or 4K sectors, but it is a possibility. And they use the SCSI transparent command set. So essentially, it uses the same SCSI commands as what you would find for a SCSI hard drive. And normally, they're pre-formatted as one partition, which we call a logical unit in USB mass storage. So you should check for additional logical units beyond the first one. One thing to be aware of, Windows, most versions of Windows, will completely miss a second partition. So if you're looking to hide some information, put it on a second partition on your thumb drive. Even better, encrypt it and use some file system that only works under Linux. Obviously, if you're going to investigate someone else's device, you should use your Linux system to read it to make sure that you're getting all of it. Another thing, you should check your reported versus actual media size. Sometimes you can hide information in those higher sectors, and there are some cheap drives out there that are known to grossly overreport their size. You use them for a little while, and then suddenly you're like, why is it not storing anything anymore? Well, by the time it's not working correctly and you figure it out, whoever you bought it from is long gone. Another thing you should keep in mind is that the 512 byte sectors need 16 bytes for error correction. So I know if you buy a hard drive, typically they lie a little bit, right? They'll say that this has got so many gigabytes, and they'll use a billion bytes and not 1024 cubed. And you're thinking, well, I've got a thumb drive now, they're not going to do that anymore. Well, they're still kind of doing that because they don't tell you that the actual available storage is less because of things like ECC. So given that it looks like a hard drive, you can pretty much put whatever file system you want on it. Most of the time they come pre-formatted with FAT or FAT32. I have seen some of the larger devices pre-formatted as NTFS, but you can put whatever you want. You can put the true flash file system, the extreme flash file system, the journaling flash file system, or one of my favorites, YAFS, yet another flash file system, and also various Unix, Linux file systems. So pretty much anything you could put on a normal hard drive, you can put here. Now, what about the reality? What is it really like? In reality, you typically have NAND flash chips, that is, and you should realize that they're degrading after about 10,000 write cycles typically. Some of the higher quality drives might have a few more write cycles than that. And most of these chips aren't even close to high-speed USB or 480 megabits per second. Also, you can only write them in blocks. So if you change 1 byte, you're going to have to read in an entire block and then make the modification and write it back out. So if your software is not optimized for this, it can be very slow. Uh, the chips on these drives are somewhat easily removed if you have a damaged drive and you want to do some sort of recovery. Sometimes you get lucky and there's a JTAG connector on the drive. That's not as common anymore. And also you should be aware that some of these controller chips steal flash memory for themselves. So they use it for themselves in order to store various items that they need. All right, so what does a hard drive typically look like anyway? Well, so here's a pretty typical hard drive. You have your connector, and this little chip here is the microcontroller. This is the specialized microcontroller, and this big chip is the actual NAND flash chip. And this is somewhat standardized. This is what we call a TSOP package, and you could actually build a device where you take and create a socket for one of these chips and then connect it to a thumb drive, or at least the parts of a thumb drive, and then you can read someone's damaged drive. You can take the chip off and read it. This is actually a little student project I'm working on at the university at the moment. If you're good at soldering, you can actually unsolder one of these chips and then solder it onto a working drive, which I've done with about 50% success in the past. Right. Other things that you might typically find on the flash drive, an oscillator, and often there's some sort of a status LED that will blink. All right. One thing you should be aware of is that there are some highly integrated drives, and I've seen flash drives where the entire thing is located inside this connector. And often they will still come with a nice big plastic case that has absolutely nothing inside of it. They'll have an IC with the 4 connections, and that's it. It's in that what's normally a spacer in this drive. Okay, so let's look at how this gets presented. So we'll go ahead and, as you may expect, we'll come out here to our terminal. So here we are at our terminal. We'll do our mod probe, USB mod, and now we can go ahead and pick a drive. I'm going to start with this one. I'm going to go ahead and plug it in, and we'll see where it ends up. It's going to end up, I believe, on bus 3. Great. So it's on bus 3. Let's run Wireshark. Go to bus 3. Start our capture. And it looks like we're getting a little bit of traffic. I'll go ahead and stop that. And go back to my terminal. Rerun ls USB. Oops, don't want to do that. Don't rerun Wireshark. And sure enough, I'm here at device 12. So let's filter on that. USB device address equals 12. And you'll notice our standard back and forth. And here's something that we haven't talked about before. Get max LUN request. So this is something that is going to occur. It's definitely going to occur on your Linux system. It's going to say how many LUNs are there? How many partitions are there for this particular drive? And in this case, it's telling me that there are 2, or that my max LUN is equal to 1. So what's going to come after this? It's going to go out and it's going to make an inquiry, and then some more stuff will happen, which we'll talk about in later videos. So here I have two partitions, and if I do an ls on my media directory, notice that I have, in fact, 2 directories which represent the 2 partitions of this device. That's all for this video. So as always, if you're enjoying these videos here at Pentester Academy, tell a friend. See you next time. Hello everyone. Welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we will continue our discussion of USB mass storage, and we'll talk about communication. How does your host talk to your thumb drive? So, as we said before, typically this is bulk only mass storage, also sometimes called BBB, because it's bulk, 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 and we'll talk about what that means in a bit, or sometimes USB mass storage, USB MS. All communications use bulk endpoints, and there are 3 phases. The first phase is what we call the command block wrapper phase, CBW, the data transport phase, which is optional depending on the command that's being sent, and then the command status wrapper phase. All of these happen over bulk endpoints, which is why some people call this BBB, because it's bulk, bulk, bulk. Commands sent to the drive are inside of a command block, which is in the aptly named command block wrapper, and then those commands are universally pretty much SCSI commands. They use a reduced SCSI command set, and if they require some sort of data transport, that happens on the bulk endpoints, and all the transactions are terminated with a command status wrapper. By the way, bulk storage devices, mass storage devices, are a little bit different in that we talked about control endpoints previously, and most other kinds of devices have all of those commands sent over the control endpoints, but these are an exception. Everything is pretty much done over the bulk endpoints. All right, so what does this command block wrapper look like? Well, here is the C code for a structure. So here's a structure I've defined. It starts with a signature. Right? You might worry about what this decodes to until you realize that it's just USB-C for a command, and it's little endian. So that's why it's a little bit backward from here. And then there's a tag, and this tag is kind of like a packet sequence number, so it associates the status with the block, the command. Transfer length, whether it's in or out, the logical unit number, or partition if you will, and the length for the command block. The 3 high bits are 0, and the rest of it has the length. And the command block is up to 16 bytes long. Typically, it is greater than or equal to 6. So the shortest command that's in use is 6 bytes. All right, so what about this command block? The command block as we said, is 6 to 16 bytes, and the command is in the first byte, and the rest of it are parameters. So for example, here I have a format unit command, which is opcode 4. It needs a LUN, right? And it has 3 bits for a LUN. And then we have format data. Is there an extra parameter that follows or not? That's what this bit tells you. The next bit tells you if there is a partial or a complete defect list being used, and then the defect list format, some vendor specific information, the interleave, and then a control character. Right? A lot of this stuff in this particular command is going to be vendor specific. Another example. Here we have a read command, something that you would want to do a lot. Once again, the operation code begins, our command block, and then we have an address, some reserved bits, and a force unit access, which means we don't want any cache. Do we want to disable paging? What's the logical unit number? And the LBA, logical block address. Some reserved bytes, transfer length, and again, a control character. So, what are some common commands that you might see? You might see format unit, inquiry, tell me about yourself, mode select, and you'll see that there are suffixes on many of these commands. The suffixes relate to how long the commands are. There are shorter and longer versions of commands. We have mode sense to determine what is going on. And then we have a bunch of read commands. Notice that some of these are marked as required. So read 10 is pretty common. Read 12 would be more common with larger devices. There's a read capacity command, a read format capacities command, and some other associated commands. Report how many LUNs you have. Test if the unit is ready. This is something that's sent quite a bit. In fact, many devices will go to sleep if they don't regularly receive these. And then, of course, we have our write commands. So we send a command. There is some sort of data transfer for most of these commands. And then we get command status, which is sent in a command status wrapper. All right, so it starts with a signature. What's that signature? This is actually USB-S for USB status. There's the associated tag. All right, so what's the tag? It's that number, that sequence number, if you will, that relates this to a previous command. Then there's a data residue. That's the difference between your requested data and the actual data that you got. In other words, is there more to come? And then we have a status bit. Now, how does the status bit work? The status bit is going to tell you 0 if it passed, 1 if it had some sort of an error, and 2 if it had a phase error. So what's a phase error? A phase error is the way that they transfer information on a USB bus. They alternate between 2 different channels, if you will, data 0 and data 1. And there are some rules for how this happens. And if you get out of sync, that's a phase error. And when you get a phase error reported, then there are rules about how you should reset. Now the fail comes from actual physical SCSI hard drives where they would have a wire that if there was an error, that wire would be toggled. And they're recreating that in USB. Now, in order to know what actually happened, you have to go in to that device. You have to query it to get the error information. Well, that's all for this video. In the next video, we'll actually delve into Wireshark and look at some of this traffic. As always, if you're enjoying your time here at Pentester Academy, tell a friend. See you soon. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to continue our discussion of mass storage communication, and we're going to do a little demo. So as a reminder, we talked about mass storage communication and how it works. We have 3 phases: the command block wrapper phase, an optional data transport phase, depending on the command, and then a command status wrapper phase. So what does that look like? Well, let's go ahead and fire up our Wireshark. We'll start by firing up our terminal, and we'll run Wireshark. I'll go ahead and grab a thumb drive. I'll just pick one out of my pile. I'm picking this one today. I don't even know what's on it. Plug it in. Ooh, actually, I should probably start my capture first. So I'm going to guess that that is on bus 3. I plug it in. I should see some new traffic on bus 3. And we'll go ahead and stop it. All right. If I do an ls USB, I will see that it is bus 3 device 14. As I've said before, sometimes it's hard to find your traffic on a busy bus. You might not have even seen any of the traffic going by for this one, but here we have our request to set the address to 14. Our normal descriptors being passed back and forth. We get the maximum LUN, and the response is that this one has only one LUN, one partition, which is part of the reason I chose this one. All right, and now what do we have? We have an inquiry that says, what is the LUN? Tell me about LUN 0. So it says, here is my command. Again, it says USB-C for command. That's the start of my wrapper. Then what is the command? The command is right here. The command is tell me about your LUN and which one? Which LUN? The LUN is 0. All right. So notice after that, there's another packet, and it says bulk out. And there's nothing in this packet. It's essentially an empty packet, and it's on the bulk out endpoint. And what this is an ACK. This is a, hey, I got that command. And then here from the host, we have another packet. on the bulk in, another zero link packet. And this says, okay, I would like to start this process. I want to start this communication so that in the next packet, I can send a response. So here is my response. To that command. Here's the data, if you will. And this is the data transport phase. And again, that's what this is about. This is about a command being sent. Tell me about the LUN. An acknowledgement. And then another zero-linked packet saying, please start sending your data. And then a data packet. Notice this is on a bulk in endpoint. Followed by a zero-linked packet, which is another ACK. And then there is a response. And it says response, LUN, inquiry, good. So if we look at this response, we can see this is the command status wrapper phase. All right, so I've returned USB-S for status, and I've returned a status of 0. It's all good. What's going to come after that? Now I have another command that you'll see a lot. Test unit ready LUN 0. Right. This is sent from the host, and this is telling my drive, are you out there? Are you ready? And this also keeps the drive alive. Then I get a zero-linked packet back, an ACK, and then I have the host sends a zero-linked packet, which means I am ready for you to send your response. Now, in this case, there is no data transport phase. So we go right to our status, right? So going through that quickly again, it sends a command. Is this ready? And again, it starts with USB-C. Command is to zero-linked packet ACK from the device, zero-linked packet to the device saying, all right, send me your stuff. And then the response is in a status wrapper. And the response was, it's all good. Okay. Incidentally, remember that we talked about the tag that associates these two packets, the command block wrapper and the command status wrapper, and that's the tag of 2 in this case. All right, now I want to read the capacity. How big is this device? Zero-linked packet, ACKing. Zero-linked packet saying, please send me your stuff. And then data transport. This is how big it is. Zero-linked packet to ACK, receipt of that information. And here we have our status wrapper. And this one has a tag of 3. Then we send a mode sense. Tell me what you're up to. Zero-linked packet to initiate the response. And here's the response in the data stage. Zero-linked packet to ACK. And then the status. So here's the status, and again, it's going to have a USB-S signature. And if you scroll down, you'll see other things. You'll see a lot of test unit ready. And you'll see some read requests. And as I said previously, there's one difference that you will notice between Windows and Linux is that Linux tends to pull a lot of information in at the start versus what Windows does. Well, that's all for this video. As always, if you're enjoying these videos, tell a friend and help us spread the word. See you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pen Tester Academy. In this video, we're going to look at USB mass storage devices and how they're handled by Windows. Now, some of you are probably aware that when you connect a USB device, it is recorded in Windows. In other words, when I connect a USB mass storage device, the registry stores a lot of information about that device. A lot of end users, of course, don't realize this. So if you're a forensics investigator, this is a good thing for you and a bad thing for them. All of that information is stored in different places in the registry. Some of the best places to start, if you look at the system hive under current control set enum USB, you'll have some information on every USB device. And there's another tree, USB store, that has information specific to mass storage devices. Also, if you look in the user hive, which is stored in their user directory, usually app data or application data, depends on the version of Windows that you're running, in ntuser.dat, under software, Microsoft Windows, current version, Explorer, mount points to, you will find information on who it was that mounted this USB drive, which can also be valuable information to have. Great, so let's do a demo. Let's actually look at this stuff in Windows. So I've already brought up my Windows registry editor, and you see here that I have a few different devices under USB store. You'll see there's a Patriot memory device, and right under this top level you will see another tree, and that tree is named based on the serial number. So this is the serial number for my device. Also in here you will find a lot of information such as what class device is it, and what driver needs to be loaded, a friendly name for it, etc. If you drill down a little bit more, you will find things such as device parameters, media change notification, logs. There's not a lot for this particular device. But you can take this information and then correlate it to information up here. All right, so I can correlate this with another device. So under USB, I can find some different devices. Here's a mass storage device. And this one, in fact, looks like a class mass storage device, subclass 6, protocol 50, which is pretty much the standard. And this will tell me all of the information that I need to know. So if we drill down a little bit more on this particular device, see its parameters. Here in this long list, we see something that ends with AA, 1D, etc. And that is a serial number. So if I scroll down here and I see that, I notice that that is a serial number for this Lexar drive, this Lexar USB flash drive. So there's a correlation there that I can see. Great. I could also go over to the user hive and find out what user has mounted these particular partitions. And I could do that. Now, of course, I can automate all of this stuff using Python. I can use tools like Ripper that you might be familiar with. Incidentally, you might expect to see some exciting Windows forensics classes coming out here at Pentester Academy sometime, and you might get more detail on how could you use Python to go in there and look at these sorts of things. Now, one thing that you can do to make this easier, there's a tool out there called USB Dev View, and this is a great tool. And here's what it does. It will tell you all of these devices that have been connected. So if you look at the kinds of information that's provided for you here, you'll see the kind of device. Is it connected now? Is it safe to unplug it if it's connected? Is it disabled? Is it a hub? And if it's connected or was connected, what drive letter was used? What's its serial number? When was it first created? When was it last plugged in? And that information is from the timestamp on the serial number key. What's the vendor ID, product ID, firmware revision, USB class, subclass, protocol, all kinds of information. Parent information, drivers being loaded in some cases, power required, USB version, supported, all kinds of great information for a forensic investigator. So that is available for you using this tool, USB Dev View. Just do a search for it. It's available online for free. We just scratched the surface here with how Windows handles thumb drives, but I wanted to start with that before we got into doing duplicates and doing some write blocking and such. I hope you enjoy this video, and as always, if you're enjoying your time here at Pentester Academy, tell a friend. See you next time. Welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to start to talk about duplication. How do you forensically duplicate a USB mass storage device like a thumb drive? And we're going to start to talk about how you can do this with a little microcontroller-based device. So in this video, I'm going to introduce the chipset that's used for that device. And that chipset is the Vinculum 2. So some of you might be familiar with the company FTDI. If you know anything about FTDI, you know that they're all about USB. So a few years back, they came out with their own microcontroller that was USB friendly. And that microcontroller is known as the Vinculum 2. By the way, they're on the verge of releasing a new microcontroller that's even more powerful. That's the FT90X series. It's not quite out there yet, but just so you know that that is coming around. So the Vinculum 2 has two full-speed USB 2 interfaces, which can either be a host or a slave. So it can be a host or a device, essentially. They also have 256K of flash memory, which, if you're not familiar with microcontrollers, sounds like very little. And if you're familiar with microcontrollers, you realize that's a lot. So that's a lot of memory for storing programs. Also 16K of RAM, which is respectable for a microcontroller. It also supports industry standard stuff such as SPI, which is a interface standard to interface with external devices. So it supports 2 slaves and 1 master on an SPI interface. It has a nice, easy to use IDE. If you're familiar with programming in C or C++, you'll probably be familiar with how this works. And it allows simultaneous access for multiple devices. Now, one thing that's nice about these chips come in surface mount only packages, which for prototyping is a huge pain in the butt. However, they do have some development modules available, which makes it easy, and these are cheap enough that you can go ahead and then embed them in the final device. All right, so what do they look like? Here's a couple of pictures. These are just a few devices I had laying around. I'm sure all of you have stuff like this laying around too. So this is what they call a V2 DIP2-32. So this is the 32 pin package. Now they have 32, 48, and 64 pin packages. And unlike the AVR series that some of you might be familiar with, what's found in the Arduinos, etc., when you go up in size to these different chips, you don't get more memory and more processing power. The only thing that changes if you go from one chip to another is the amount of I/O that you get. So this allows me to run the same program on all of these chips. So this is the 32 pin chip. So this is a little module. V2 means Vinculum 2. DIP2 means that it has 2 ports here. This one is a DIP1. It only has 1 port. So it depends on what you're trying to do. If you want 2 hosts or a host and a slave, or who knows what you want. This is the same thing with the 64 pin package. So notice that it's just bigger. This is a nice breakout. Here it is on my prototyping board. And here's the same thing, but with only one connector on the end. This little guy here is a debug module. This is used to program these development modules. You'll see these connectors here on the end, and that's what that is used for. This just connects right there and you program it. We'll see how to do this in future videos. This here guy is a Vinco. It says Vinculo here, but they had to change the name for copyright reasons. This is their version of the Arduino. So if you look at this, you might say it does look kind of like an Arduino, except it has an extra row of pins because there's a lot more I/O available on the Vinco. And another difference is that it has the same port. So while you do see 2 USB connectors here, a slave and a host connector, this is how you program it. You don't program it over USB. So that's another difference from the Arduinos. Incidentally, I don't really recommend this Vinco module. We'll talk about it more in future videos, but I wanted to like it, but I've had a lot of problems with it in terms of timing and the way that it powers up these different ports. So that's just a little FYI there. Okay, how does it look like internally? Internally, you have your input-output multiplexing, and then you have a whole bunch of different kinds of interfacing. You've got UARTs or serials, pulse width modulation, SPI we talked about a little bit, GPIO, timers, all these things that come in on this peripheral bus. Then you have your kind of core functionality. And notice that also in here, we have our 2 USB ports. And all of this stuff is handled for you internally. So it has this nice IDE. Here's a little screenshot. And here's another screenshot. So if I'm creating a new application, I can tell it, hey, this is the package that I'm using. Please set it up this way. Set this pin to do this function. All right, so how does this look in actuality? Let me go ahead and I will bring up VirtualBox. So here we have our IDE, and I can say I want to create a new project using the app wizard, and I can give it a name. I'll just say I'm going to put this as being here, and I'll call it project 42, the answer to life, the universe, and everything. And I can say I want to target the Vinco, an evaluation board, discrete chips, or one of these modules. I'll just go ahead and say I want to target this module, and I want to target both the 32-pin and 64-pin version. What sort of drivers am I going to use? I'm going to use a host driver, and we'll go into this sort of stuff in more detail. And you might say I want to use the bulk only mass storage device, etc., etc. So then I can go to my IO mux. I can look at a pin and say this is the signal I want to use. This one actually was a bad choice because it's for the debugger. And I can set up these signals to be used for different purposes. The other thing that's nice is I can toggle between the 32 pin and the 64 pin. And I can have my program that works with both. So I can use either one. And we'll see how that's done in our projects that we're going to come up with. Other nice things about the Vinculum, it's multi-threaded and it runs at a decent speed, 48 megahertz. If you might have tried to do some of this USB stuff with a slower chip, and here at 48 megahertz, you're 4 times the speed that is the highest speed that you can support, 12 megabits per second, and that's about the limit. You don't want anything slower than that, so some of the Arduino chips, the AVR chips, are a little slower than that, and I can set up multiple threads in my program. So that's just a brief introduction to the Vinculum 2 and the environment. That's all for this video. And as always, if you're enjoying your time here at Pentester Academy, tell a friend. We'll see you next time. Hello, everyone, and welcome to Pentester Academy's version of USB forensics and pen testing. In this video, we're going to start to talk about a simple duplicator. How could I very simply, without a computer, just using a small microcontroller-based device, create a forensic duplicate of a USB mass storage device, a flash drive, if you will. So let's talk about the hardware. We introduced the Vinculum 2 last time, and we can use something like this. This is a V2 DIP2-64 in this case device, which means that it's a Vinculum 2 chip with 64 pins on the chip. We can also use the 32-pin chip, or we could even use the 48-pin chip. So we'll show you how to do that. A little bit more about the hardware. This device is nothing more really than a breakout for the actual chip itself. So there's not anything really interesting to see there. So high-level design. We're going to start out really simple, and then as we go, we will refine this design and make it a little bit better, and we'll add things such as a user interface so you can see what's going on. But essentially, we're going to start with something very simple. You insert a flash drive to be copied, and then you insert a target drive for the copy. Right? Ideally, you'll use the same model, and it should be at least the same size. It's okay if it's bigger, but not smaller. And it should have the same block size. Typically 512 byte blocks are what are used. And then a sector by sector copy is performed. Now, when I say it should be the same size or bigger, one of the reasons that I say it should be the same model, you have to be careful. We talked about in the past that sometimes these devices might say they're 4 gigabytes, but the controller uses a little bit of that storage for itself. And there are other little minor differences. So you don't want to be one block short at the end, basically. So you can do a sector by sector copy. It should work on most drives, and it requires a little bit of time, however, because of the full speed limitation. It takes about 11 minutes per gigabyte. So you wouldn't want to use this for something that's huge. Like if you have a 128 gigabyte flash drive, I don't recommend this technique. But it is nice for kind of getting started and getting your feet wet a little bit. And it's really the writing speed of the target that is going to be the slowing factor, the bottleneck, if you will. All right, so let's see how this works out in our VirtualBox. So I've gone ahead and I've loaded up the IDE here in my VirtualBox, which is running Windows XP. And I will just go ahead and say, I want to create a new project. So I'll create a new project. I'll use the app wizard. And I'm going to call this one the simple duplicator. And I will put it here. Simple dupe. Solution 1. Click next. By the way, clicking next has the same effect as going from one tab to the next here. And I will use, for my case, the v2 dip 1. I'm really using the 2, but don't worry about that. And I'll give it 32 pin and 64 pin. Next. And I'm going to be using 2 hosts. GPIO I might want in the future. So I'll go ahead and say I'm going to use GPIO port A and port B. I'm going to use the FAT file system. And I'm going to use bulk only mass storage device for both interfaces. And that should be sufficient for that. Here is where I can set up my different I/O pins. So now that I've said I want to use some GPIO, I can establish what each pin will do. At this point, we're not going to get into that yet. Right now, we're just talking about how do we create our application, and then we'll start developing this application very quickly. So for now, I'm just going to hit next, and I can set my CPU speed. Normally, I would leave that at 48. Lower speeds mean lower power, but we're not concerned about that. Honestly, the power is going to come from the thumb drives. They take more power than this chip does. And if I hit next, I have the ability to set up multiple threads. So normally there's one thread that's run and created automatically, and there's a function called firmware that'll be created. If I click next, now I get a summary telling me about the application I'm about to create. I'll go ahead and click finish, and it's unhappy with me. So let's go ahead and change this. And there we have it. All right, so I have my files over here. If I collapse the FTDI libraries, I'll notice that I have just a few files left. I have simpleduplicator.c, and they have nicely created a shell for me that will set up all of the things that need to be set up, such as handles for the different devices. There will be a call to IO mux setup. And that's a function that was created when I was saying this pin does this. My main method is going to set up a couple of things such as initialize the scheduler for the multi-threaded capabilities. It creates an idle thread. It will initialize my different drivers and interfaces. It will create a thread that runs the firmware program, and it starts the scheduler. Once it hits the start scheduler, it never returns. It just sits here in its loop forever. And there are a couple more functions that are created. But the one that you're interested in, the one that you're going to override, is this one here called firmware. Real quickly, if I look at my header file, I will see that it doesn't have much. It has a bunch of definitions for numbers, constants that go with each of these drivers, basically what device number it is. I don't need to concern myself with that. And then if I look at this IO mux setup, I will see that it says if it's 32 pins, do this. If it's 64 pins, do this, because those are the two packages I told it I wanted to support. Well, that's all for this video. In the next video, we'll start filling out some code, and we'll show you how you can read and write to these mass storage devices and program your hardware, etc. As always, if you're enjoying your time here at Pentester Academy, tell a friend. See you next time. Hello, everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we are going to continue our work on our simple duplicator, and we're going to go through the code that you need in order to connect, read, and write from your duplicator. So what's involved here? Well, in order to accomplish this, we're going to need to add some code. So here's the code that we had previously. In a previous video, we set up our code using the wizard. And all of this code that you see here is generated for you by the IDE. And recall that normally there's a new method called firmware that gets set up, and it's this new method that does all the things that you want your application to do. So if I walk you through this, I start out by defining a couple of variables. We have a sector size for both the source and destination drives. We have a connection state, a status variable, and then a few variables set up for USB hosts. So we have a device handle for interface and a few other things. And again, these are going to be set up almost automatically for you. Great. A couple other things of note. We set up a semaphore. A semaphore, if you're not familiar, is used to synchronize access in multi-threaded applications. At this point, we haven't gone multi-threaded with our application. However, behind the scenes, it is being multi-threaded by the FTDI libraries. So that's something you should be aware of. Their libraries are going to multi-thread some things. And we first create a host controller. So we have to open our host, which is host 2. That's the port that we're using for our source. And we create a buffer of our buffer size. For now, I've set my buffer size to be 4K. Remember, there's only 16K of RAM, so that's a good chunk. It's typically 8 sectors long. And then I have a big do loop. So what am I going to do in this do loop? I'm going to first delay to give it a little time to enumerate and connect, and then I'm going to check it. I'm going to make a IO control call, and I'm setting it up here, and I'm saying, here is the thing I want to do. I want to get my connection state, and I set the get variable in the structure equal to the address of connect state, and then I make the call. By the way, all of this is well documented in the Vinculum 2 installation guide, user's guide, and all of the different documentation that comes from FTDI. So you might look at this and say, wow, I would have never thought to do it this way. It's also very C-like. If you do a lot of low-level C coding, this might look familiar to you. Otherwise, this might look very confusing to you. So most of the calls into the libraries are done using IOCTL calls. So here we check and we say, is it enumerated? If it is, now let's see if it's actually a bulk-only mass storage device, or BOMs in FTDI speak. So we set up another call where we want to get device and find a device by a class. And that class is going to be mass storage, SCSI, and bulk only protocol. So we're going to just double check to make sure that someone didn't plug something else into our port. And then we say, if that's not okay, for now we're just going to break out of this loop. Later we'll add some LEDs and messages and such. Now we open our device. And we attach to the device. So that's the next command that we send to it. And once again, we check. We make sure that that all works successfully. And then we'll get the sector size. It's probably 512, but we want to make sure. If it's not 512, it'll be some multiple of 512. And we set the address of sector size 2, the sector size for port 2, equal to the get variable in the structure. We make the call, and now we have the size, the sector size. We do something very similar for the second port. Now that we have the first port enumerated, we are going to check the next port. And if it's not enumerated, we'll just sit here in a little loop. There's a delay of 1/4 of a second in here so that it's not a super tight loop. Give it a little bit of time for you to plug something in and have it enumerated. And we do the exact same thing. We say, okay, is it in fact the right kind of device? Is it a mass storage device, SCSI, bulk only mass storage, etc.? If not, I'm going to break out. If it is, I'm going to try to open a bulk only mass storage device, attach to it. Once again, get the sector size using this call. And I'm going to set my cluster size equal to the buffer size divided by the sector size. This should always be some multiple of 512. In most cases, it's going to be exactly 512. But this is just so that we can make sure that everything is lining up properly. And now we're finally ready to go. So we have these two semaphores. We have one for reading and one for writing. Again, these are used internally by the FTDI libraries. This is not something we actually have to deal with ourselves at this point. And we will set our sector equal to our starting sector. We have a pointer to our buffer. The total length, the maximum length we want to transfer, is equal to the buffer size. The buffer length is equal to the buffer size as well. Our status is we don't know yet. And we give it a pointer to our semaphore. And we say, please do all phases of this next bit. All phases means the command phase, the data phase, and the status phase. And then I call a function, which we'll look at in a second, called fatReadSector. I read in the buffer size. If it's okay, I write it out using fatWriteSector. Otherwise, I say I'm done, and I break out. Now, by the way, I don't know how big this media is. Because of some limitations in this library, it's actually not easy to do. So for now, what we've done is we've just said we're going to keep on reading until there's an error. If there's an error, we're going to assume it's because we hit the end of the media, and then we're going to stop. Now we go to the next sector. Well, which sector is it? It's whatever the current sector was plus the cluster size, which is probably 8. We keep on going while our status is okay and we're not all done. You'll notice I have a little comment here that says, hey, you should really do this better, but we aren't going to do that for now. And then once we're done, we detach and power down, and that's it. We're done. And that's how you can tell that it's over. We're going to talk about how you can add status really soon, but for now, we just wanted to look at what's the code involved in this duplicator. Not very much coding here, thanks to support from the libraries that come from FTDI. All right, so what are these read and write sector methods look like? Well, here, by the way, these also come from example code provided. We say, here's a sector. Here's a pointer to a buffer where we can put our information and how much stuff do we want? How much do we want to read? And so we set up our transfer structure. We give it the sector, the buffer, the length. We set our status. Once again, we have a semaphore for coordinating the actions. We say I want to do all phases, and then we call vos dev read and give it the handle to this device, our bulk only mass storage device, number 2. And here is our pointer to our exfer, our transfer structure, and the size of that structure, and then a null. If the status return was okay, then I'm going to reset that status to fat okay, which turns out it's actually the same value, but that could change in the future. And then I return the status. You might say, where did my data go? Well, my data went right here into the buffer, because remember I gave you a pointer to the buffer input. And if I look at the write method, it's very similar. The only difference is I can call vos dev write instead of read. Other than that, the same. All right, well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, tell a friend. See you next time. Hello, everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to talk a little bit about blinking LEDs, which maybe if you're a Raspberry Pi user, you're familiar with blinking LEDs, because honestly, that's about all they're good for. But that's a topic for another video. All right, so let's talk about microcontrollers and what we call GPIO, general purpose I/O. So general purpose I/O involves toggling voltages on pins. Now, one thing that a lot of people don't actually realize is this is done by ports, not by pins. And what does that mean? You might have multiple pins that you can toggle, but those pins are glued together in ports. So if you're an Arduino user, I'm sure there's some of you out there who are, you might say, but Phil, you're wrong. I know that I can call methods in my Arduino processing sketches that will set pins, set them high, low, input, output, etc. And that is correct. However, if you look at the underlying AVR chips in your Arduino, what you'll find is that those chips really deal with ports, and it's just a layer on top of that that you're using with the Arduino libraries, if you're using processing, that is. Now, many of these pins can have more than one function. We talked about the FTDI Vinculum 2 chips earlier. We said there are different pin capabilities, different configurations. There's 32, 48, and 64 pin packages. And the only difference was how much GPIO did you want. So if you need more I/O, you get the larger package. However, even if you have the largest package, each pin could be performing one of several functions. So in order to determine which pin is doing what, if you're not using the default function for that pin, you have to program it. And you have to program what's called the multiplexer. And the multiplexer is really just this piece of the chip, if you will, that says, what did you want to use this pin for today? Some other things you should be aware of when it comes to doing GPIO with microcontrollers. It might be 3.3 volts or 5 volts. 3.3 volts is much more common. The only reason that you see 5 volts is that that is the USB voltage. But if you look at the actual microcontrollers, they tend to be 3.3 volt devices. So you wouldn't expect a 5 volt output from such a device. Now, the inputs can either be 3.3 volts or 5 volts, or what you might see is something called 5 volt tolerant, but it's really 3.3 volts. What does that mean? That means if you put 5 volts on an input on this microcontroller, it won't blow up. Be very careful. Now, it turns out that the Vinculum 2 is 5 volt tolerant, but some of these chips are not. In particular, if you're working with something like an XB radio, it has an embedded microcontroller, as many devices do. It is not 5 volt tolerant. So as soon as you put 5 volts on one of those lines, you might be buying a new chip or a new device. So something to be careful of. What about the Vinculum 2? Well, the Vinculum 2 divides things into 5 different ports. Now, some of these ports have extra capabilities, such as interrupt handling. In particular, some of the pins on port A can be used for interrupt handling, so you can toggle them, wake things up, and do such things like that without having to pull all the time. And you have to set each pin to input or output with the multiplexer. So there is a call that you will make, and we'll see that in the next video when we'll talk about the software side of these things. So there's a call that you make, and it tells the multiplexer, hey, this pin is being used in this port as an input or an output, and that's the way it's used today. Also, you have to set the port mask for whatever port you've associated that pin with. This will make more sense when we look at an actual example of how this is done. If you have a pin that's set to output in its associated port, in order to toggle its value, to change the value from high to low, or vice versa, you just need to output the appropriate value to the port. And all pins that are outputs in that port will simultaneously change depending on whatever value you use. So this is another thing to keep in mind. You can't just say, well, I wanted to set this one bit, so I'm going to set out an output that includes that one bit. You might mess up the output on some other pins in the same port, and we'll talk about how to do that soon. All right. Let me give you the 1-minute tutorial on LEDs. What's an LED? It's a light emitting diode. You can think of them as very efficient lights. It's a diode. So what is a diode? A diode is something that has electricity flowing in only one direction. So if you look here at the bottom of my slide, you'll see that here's the electrical symbol for a diode. It looks kind of like an arrow, and the electricity only goes this way from plus to minus. And you'll also see that there are arrows coming out of it. Those arrows coming out of it represent light. It's a light emitting diode. Now, when light or voltage is applied across this diode in the correct direction, there's a standard voltage drop. And that depends on the color. It's normally between 2 and 4 volts. It's important to know what the voltage drop is for a couple of reasons. If it's 4 volts and you only have 3.3 volts, it's never going to light up. And if it's 2 volts and you have 3.3 volts, you may require a current limiting resistor because the brightness of the LED is determined by how much current flows through it. Now, there are several online calculators for these, such as ledcalc.com, that you can use. I won't go into all the theory, but basically, if you have a certain voltage you started at, and then you have a voltage drop that depends on the style of LED and its color, once you drop the voltage out, if you have a current limiting resistor, you need to figure out how big it has to be for that remaining voltage to be used up, if you will, in that resistor. Right. So there are a couple of ways you can calculate that. And again, it's important with some microcontrollers that you do limit the resistance with resistors. Otherwise, if the current gets too high, it can damage your microcontroller. Turns out that the Vinculum 2 doesn't have this limitation, but I thought I should point it out to you in case you're dealing with some other microcontrollers. The other thing you need to be aware of, LEDs are polarized, right? It's a diode, so it only goes in one direction. And here is a top view of a typical LED. And if you feel it, you'll notice there's a flat side. That's the negative side. So when you're going to install it, you need to make sure that you install it the right way. Otherwise, it won't light up and it does nothing. It's essentially a short. If there's no limiting resistor, it could be a really bad thing. Other times, you can tell the polarity by looking at the length of the leads. The longer length lead is the plus one, and the shorter one is the minus one. Also, if you look at it from a side view, you can see the anode and the cathode, and they look a little bit different. All right, so what about LEDs for our situation? Here is my simple duplicator, and this has a 32-pin package, Vinculum 2, and here are the two connectors. And you can see here I have installed 5 LEDs. And these 5 LEDs are installed directly onto various pins. And all of this is super glue, which I installed just to keep it all rigid so that it doesn't fall apart on me, especially if I throw it in my pocket. This is a power connector. The power connector is set so that it can work with this guy. This is my portable power supply for that guy. Great. So that is how we can add some LEDs to our little duplicator. And that's all for this video. In the next video, we will go over the software side of this equation. As always, if you're enjoying these videos, tell a friend and help us spread the word about SecurityTube. See you soon. Hello, everyone. Welcome to USB Forensics and Pen Testing here at SecurityTube. In this video, we're going to talk about how do we add LEDs to our duplicator. In the last video, we showed you a little bit what was involved in terms of hardware. So let's show you in this video what is involved with the software end of this. So here I have my nice simple duplicator that we've talked about in previous videos. And to this, I'm going to go ahead and add the LED functionality. So this is not going to be terribly sophisticated at this point. We still haven't optimized it, excuse me, or anything like that, but we are going to add some blinking LEDs. So at least you'll have some indication what's going on. So the setup, the wizard, will automatically create for me something such as this. And this is a method that's called IOMux setup that automatically gets created and called by the wizard. And you'll see here, I'm setting up a few pins, and I'm associating these 5 pins for my 5 LEDs with port A, pins 3 through 7. And all that I'm doing here is I'm defining these using this method, VOS IOMux define output. By the way, VOS is the Vinculum operating system. So you might see a lot of methods that start with VOS. Here's the pin, and here's what I want it to be. I want it to be an output for port A6. If I go and look at my main function here, my firmware function, go ahead and scroll down there. You'll see for my firmware function, I've added a few things. So here I added an array for my LEDs, and all these are addresses for each bit, the appropriate bit for my LEDs. And so I start out with 8, and then 10 hex, 20 hex, 40 hex, and 80 hex. So you can see all I'm doing is I'm just shifting to the left a bit as I step through those. So now I have the same code that we've seen before. Here I delay, and after I've delayed, I'm going to start to blink my LEDs. I'm going to start with the first one, LED 0. And I'm going to write the value to my port for port A, my GPIO port using VOS dev write. I'm going to delay, and then I'm going to write it again. And this time I'm going to turn it off. So what is this going to do? This is going to wait, turn it on, quarter second later, turn it off. And then I'm going to proceed. Why is it going to turn it off? Because I set LEDs equal to 0. And then I wrote that value out. Again, if I look at my array, here's my first LED. It's associated with pin 3 on port A, so that's called A3, etc. And if you remember from pictures last time, I actually made this a different color. So I made the first and the last LED a different color. Now, if it's enumerated, I step to the next LED. And I try to make a connection. If I'm unsuccessful, before I just broke out of here, in this case, if I'm unsuccessful, I'm going to illuminate an LED, delay, and then I'm going to break. Here, I have LEDs set to LED 3. I'm going to illuminate it, and I'm going to break. So again, if there's an error, I'm going to light up that particular LED. Now I'm going through the second drive. I have my source drive, and this is for the target drive. So the target drive, I'm going to do something very similar. Delay, light up the second LED, and turn them all off. If my LED, I'm going to set it equal to this. I'm going to turn it back on again. Now I'm going to try to connect. Again, errors are reported by illuminating an LED and then breaking. So all of this is fairly boring, right, and somewhat repetitive. Incidentally, something you will notice if you look at some of the sample code with this class, you might look at some of this code and say, gee, Phil, your coding sucks, which may be true. But one thing you should be aware of with little microcontrollers like this, making lots of function calls is costly. Right? You normally don't think about what's the cost to switch context to a new function, but it turns out that it can be fairly high on a little microcontroller that's running at 48 megahertz. So that's one reason we try to avoid that. You might also notice that I reuse counting variables and things like that. That's another thing that you'll see that, generally speaking, if you're used to PC programming, you might think, well, this guy's a bad programmer or he's just plain crazy. But you'll see things like that a lot more often in microcontroller code such as this. All right, so now is where we get into the really weird stuff. All right, so here, what I'm going to do as it's copying is I'm going to strobe these LEDs. So I have this very funny looking loop here where I say for I equals 0, I less than 500, I plus plus. I'm going to read a sector. If it's okay, write a sector. And if there was an error, I'm going to set everything to all done. I update the sector based on the cluster size as I did before. Now here's the only thing that's changed. I have this little inner loop that looks a little strange. And then I have this LED step plus plus. And now I'm going to update my LEDs. I'm going to write out LED and then LED step mod 5. So that's the modulus operator. So essentially, I'm going to divide by 5, and this is my remainder. So I'm going to get an answer between 0 and 4 here. And I'm going to write that out. And what that does is it allows me to update these LEDs. So it'll step through the LEDs as it writes without burning up a lot of CPU cycles. I don't want a nice tight loop or anything like that. Again, if there's an error, I'm going to illuminate certain LEDs and break out. And when it's done, I'm going to turn them off. I'm going to turn off the LEDs here. I'm going to say LEDs equals 0. I'm going to write that out. And then I'm just going to plain old power down the device. And then I'll know, yes, it's done. Well, that's all for this video. Hope you enjoyed it. And as always, if you are enjoying your time here at Pentester Academy, please tell a friend. See you next time. Hello, everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we are going to look at uploading programs to our duplicator that we've discussed in previous videos. So we're going to do this. We're going to have to program our Vinculum 2 chipset. And the way that we do this is we use a debugger module that's available from FTDI. By the way, you can do this without the debugger module, but it's really not worth the effort, in my opinion, to save $15 to make your own debugger module. Something you should be aware of, you might need the FTDI FT232R device drivers in order to talk to the FTDI F232 chip on the debugger module. So keep that in mind. If you're not having any success or Windows is complaining, then you might need to go to their website and download the drivers. Also, if you're running in VirtualBox, you might need, well, you will definitely need the extension pack and an appropriate USB filter. And I'll show you how to do that in a little bit here. Another thing to keep in mind, your programs are stored in NAND flash memory. We've talked about limitations of NAND flash before, and one of those limitations is that you have only 10,000 writes or so before it fails, which might sound like a lot, but if you're one of those people that writes a line and uploads, writes a line, uploads, you'll actually get there sometime before you're done. All right, so here's a picture of my little device. So here we have our module, and I've chosen to use these 5 pins right here at the end, which are labeled IO 5 through 9, and right next to them there's a ground. So there's a ground connection here, which goes to my ground bus on my little circuit board, my breadboard. And this is the debug module, which is being attached. Now, in addition to using this for programming your device, you can also use it to power your device, which comes in very handy when you're working with it. And of course, this is my USB cable. So let's go ahead and show you what this looks like. And I'm going to start out by showing you VirtualBox. So here is my Windows XP is what I'm using for this virtual machine, and a couple of things you need to make sure of. Number one, install that extension pack. Make sure that the extension pack version exactly matches the version of VirtualBox that you're running. So if I go here and I look at my version, it's 4.3.18, and you better make sure all of that lines up. If it doesn't line up, doesn't match exactly, you're going to have issues. If I go to settings, there's a USB setting, and you'll see right now this is running, which is why this is grayed out. But I have enabled USB and enabled USB 2.0. In order to do that, I had to make sure that I installed that extension pack. If you don't install the extension pack and you try to click enable USB 2, it will tell you this is incompatible settings. And you see I already have my debugger module here. And here's how you can add a new module, a new filter. You just click on the plus, and it will look at all of the attached devices. Just click on that device, and you're good to go. And that will automatically be passed through. So I'm going to hit cancel, and I'm going to go ahead and bring this up. So here is my virtual Windows XP system. And again, if I click on devices and go to USB devices, you'll notice there's a check mark here. I can uncheck this and you'll hear the little tones indicating that this has become disconnected, just like I unplugged it. All right, I'll go ahead and I'm going to run up the IDE. Click on the little button in the corner. I'll open my recent project. And here is my project. Now, in order to build it, if you click on the Build tab, you can click on Make or Build. I've already just built it, so everything's good there. And you can either build a debug or release version. For our purposes, it doesn't really matter right now. If you click on Debug, you want to check and make sure that it sees a debugger. If it doesn't see this debugger, if you click on the check mark, you can refresh the list of possible devices. Again, if it's not working, check and make sure that you have those FT232 drivers installed. All right, so once you've built it, all you have to do is go ahead and click on Flash. Once you do that, you'll see a message down here saying that it's erasing the flash and it's getting ready to flash 173K. You might recall that there are only 256K bytes of flash memory. So I'm using a good chunk in my pretty simple program. So it's something that you need to keep in mind when you start doing a lot of stuff with USB in these modules. I've never quite run out of memory, but I've gotten very close to running out of memory before. All right, and that's all there is to it. That's how you program these modules. Now I can go ahead, if I want to run my program, I can click on Start. And once I've clicked on Start, it will go ahead and attempt to run my program. You can't see it so well here, but my device is now running. Let's see if I can successfully bring it in here. You'll see, I don't know how well you can see the flashing red LED, but that's the blinky message that says, please insert the source drive, and from there you can insert the target drive and be on your way. Well, that's all for this video. As always, if you're enjoying your time here at Pentester Academy, tell a friend, help us spread the word. See you next time. Hello everyone. Welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to talk a little bit about improving performance on our simple duplicator. How are we going to do that? Well, what we're going to do is we are going to use threading and buffering in order to make this a little bit faster. As we've discussed before, writing to a flash drive is pretty slow, so reading ahead and using threads can improve our performance. In addition to doing that, we're going to use double buffering. So we're going to have two read buffers and two write buffers, essentially. And we'll use semaphores in order to coordinate the threads in our new process. So how does this work? Well, let's have a look at our code that we've modified a little bit. So here's our code in our IDE. And what's going on with our code? We have the normal stuff. We're including our header files, define a bunch of constants. Again, all of this is done automatically for us by the wizard. And now, since we have two buffers, I've decreased my buffer size to be 2K. Again, there's only 16K to play with here, so you don't want to be too greedy and starve out your program from memory. And I have all the standard stuff. And the thing that I've done is I've added two threads, which I've creatively called thread 1 and thread 2. And I have a function for each of those. So there's a prototype for those functions. And if we look at the main function where everything's being set up for the different threads, you'll see that I've just added here toward the end these two lines. So I'm going to create my threads, give them each 512 bytes of memory for their stack, and I'm going to run the function thread1 and thread2, and I've given them the names thread1 and thread2. All right, so our firmware function, that thread, doesn't change very much. I have 2 buffers now that I've added. I open all of my devices as usual. I still have the same code for my LEDs that we added last time. I make a connection. All of this is unchanged. I connect to both devices. Make sure that they're the right kind of device. And now I get to time to copy. And here, notice that I have a buffer semaphore that's being used. And look at this. What does it do? Nothing. All it does is wait until all done is set. So what we've done is we've taken all of the reading and writing out of this function and put it in the other threads. After it's complete, then it's just going to go and detach and close out the program. All right, so we have our fat read and write. Again, those are the same. So here's the only thing that's different. All right, here's my thread 1. So thread 1, I have the first sector. Again, it's double buffered. So I'm going to start at 0, and then my next buffer is going to start at cluster size, which is probably 4 in this case, since my buffer has been decreased to 2K. And while I haven't enummed the second drive, I'll just delay a second, and then I'll try again. Remember that the other thread is going to set this variable. Now, some of you might say, oh, multi-threaded, you can't do that because you don't have a semaphore that's protecting that variable enummed. But remember that only one thread is writing to it, and the other 2 threads are reading from it. So there is nothing that's going to happen that's going to end badly, right? As long as only one person is writing and the other person is reading, we're still good. We have that same funny loop, and now we have something new. We call wait semaphore on that semaphore for the buffer. So this will wait until that device, both devices, are completely enumerated and attached and ready to go. Once that buffer is available, that semaphore buffer is available, it will call a lock on a mutex. So it's going to lock this buffer so that nobody else can touch that buffer. It will read a sector in, storing it in the buffer, unlock this mutex that's for this buffer. And if that was correct, if that was good, then it's going to wait on a second buffer. It's going to wait on that semaphore. If it is not blocking, in other words, if it's ready to go, it's going to lock the second buffer's right semaphore, the mutex, read in the sector, and then unlock. Then it updates the sector numbers. So this part isn't really changed other than the fact that we now have 2 buffers that we're reading into. Similarly, if I look at thread 2, what is it going to do? Thread 2 is going to lock this buffer semaphore, this mutex semaphore. It's going to write and then it's going to unlock. And then it's going to signal the other semaphore. What this does, the signaling causes the other semaphore to be released, which allows thread 1 to run, effectively reading in a sector or a cluster. Then, if this worked okay, it will lock the second buffer semaphore, and it will write that sector or set of sectors out. And then it will unlock that semaphore. And similarly, it will signal sembuff2, which causes the code in thread 1 to continue. So let me just zip back there real quick to remind you of how this works. So here, I'm waiting. I'm waiting for that buffer to signal saying, okay, you're good to go. Once that happens, I lock this mutex, read in the sector, unlock the mutex. And when I do that, it will cause this code to run, and I'll do the same thing here. I wait. So this thread is waiting on semaphores, and this thread signals those semaphores. And there you have it. So you have these two threads working together in order to write out this information. All right, so thread 1 reads and thread 2 writes. And here we do protect the access to the buffer because it's a buffer. It's not just a small value that only one person is accessing. So we don't want someone to be changing this while we're writing or reading from it. And really, that's all there is to it. By doing this, we actually can speed up this whole process by quite a bit, given the I/O wait times for our device, especially if our target's a flash drive. Well, that's all for this video. As always, if you're enjoying these videos, tell a friend. See you next time. Hello, everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to talk about how we can add an LCD display to our simple duplicator. So far we've created a duplicator that had little blinky LEDs, which is okay if you know how to speak blinky, and a little bit hard if you don't know what the flashing LEDs mean. We also made the duplicator better by adding threading and buffering in a previous video. So now I want to talk a little bit about LCD displays. So there are many little LCD displays available in different sizes. You can get them in 1 line, 2 line, 3 line, 4 line, different configurations. So there's quite a few configurations available. The most common by far, however, is a 16 by 2. 16 characters by 2 lines is a pretty standard size. Now, regardless of the size that's used, there is a standard way of wiring these devices. They typically have 16 wires, and that's the standard that's used. So they look something like this. So here's a pretty standard LCD display. You'll see here near the top that I actually have 16 connectors. Some of them might have those connectors on the bottom, some are on the top, and it just really depends on the brand that you buy. But they're all standardized. Yeah. So thankfully, everyone knows how to talk to these, in part because they're very popular with things like the Arduino, which, if you're not familiar, the Arduino is a very popular microcontroller platform. So we're using another microcontroller from FTDI to develop our devices. All right, so what about these 16 pins? Well, here's a breakout of those 16 pins. So we have, at the one end, we have a ground pin. And then we have our voltage supply, which is typically 5 volts. You might see some that are 3.3 volts. And then we have this guy, VEE, and you're thinking, what is that? All right. VEE is a contrast control. So basically, we'll show you how to wire this up in a bit, but this controls the screen contrast based on the voltage you apply. RS is used to select things. RW, read write. EN, enable. And then we have 8 data pins. And the last 2 pins are plus and minus voltages for our backlight. So if we have a backlight, here's where you power it. You know, this would be typically ground, and this would be some sort of positive voltage, maybe 5 volts. All right, a little bit more about those signals. Again, you have the first pin is a ground, and then the supply for the logic of the LCD, contrast adjustment, and the fourth pin, the RS pin, tells you if it's a data or command that's being sent. And if it's high, if there's voltage applied, it's data. If it's low, it's a command. And then pin 5 is read or write. Are you just reading from the display or writing from the display? You can do both programmatically. Then you have an enable, and then your data bus, and then again, the power pins for your LCD backlight. All right, so a little bit more about how these are connected. Typically, you don't use all 8 of these pins. We only use D4 through D7. And you might say, why would you want to do that? You have all those pins available. That's true. However, if we think that this is being used by a microcontroller, a lot of microcontrollers don't have unlimited GPIO pins. You know, we have quite a bit available, even with a small package of the FTDI Vinculum 2. But if you're looking at a little AVR chip, such as what's found in the Arduino series, you don't want to waste a whole bunch of lines just for your LCD display. So it turns out there's a mode where you can send 4 bits or 1 nibble at a time. And that is typically what people use with these. So they have to send 1 nibble and then the next nibble, but it's not so bad. It's not so bad to do it that way. It's a little bit slower, but no one's going to notice. But I've reduced the number of lines that I need by 4, so it's typically done that way. You know, if you look at it another way, I have 4 plus 3, so I already have 7 lines that I need to use in order to get this to work. All right, let's talk a little bit about the contrast, what's labeled VEE here. Typically, if you have a potentiometer, or a variable resistor, if you will, if you connect one side to 5 volts and the other side to the ground, the middle connector, or the wiper, if you will, is connected to VEE. So you can adjust the voltage that goes to VEE. Most of the time, people use about a 10K potentiometer, 10K pot is typically used here. So that's how you use an LCD. In the next video, we'll show you how you can code it to work with your duplicator. So that's all for this video. As always, if you're enjoying these videos, tell a friend. See you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to go over adding an LCD display to your little duplicator. And in particular, we're going to talk about the software, what's involved with the software. Now, as we said in the last video, typically we only write one nibble at a time. So it goes kind of like this. If I want to write a command or data to my screen, I send the high nibble and I select either registers or DRAM using that RS line. I enable it, I toggle the voltage on the enable line, and I write the low nibble and I do the same thing. I select either registers or DRAM, depending if it's a command or data, and I toggle the enable line. All right, so that might be confusing, but don't worry, because we're going to do a demo. So what does it look like if I show you the code? So the code looks kind of like this. All right, so here I have my IOMux code. So in my IOMux code, I've started to use another port. I added port B. Recall that we're using port A for the LEDs. Now what I've done here is I said I'm going to do this with a 64-pin package. So I'm going to keep the code I had for the 32-pin package using just the LEDs. And if I have the 64-pin package, I'm still going to use the LEDs. I'm still going to have those, but on top of that, I will also add code for the LCD screen. So I'm going to use port B for the LCD screen just to keep it simple. And you'll see here that I've chosen B pin 0 to be DB4. And then I have 5, 6, and 7. Those are those 4 data pins. I have pin 4 used with the RS, that pin that determines whether or not I'm writing a command or data. And then I have my enable pin on 5. Here, if it's a 32-pin package, I don't define anything for port B. So that code will just get ignored. All right, going back over to my main file, you'll see I'm setting things up here. I still have my codes for my LEDs here. I've defined the different pins. I've added a driver for port B. So you'll notice that I've added code in my main method to initialize that port. Nothing else really changes other than I've added some helper functions. So here's a helper function that will write an LCD command. So I take a handle to my LCD. Basically, this is a handle to port B. And I take a byte that I want to write. And I shift it 4 places. And then I AND that with 0F. In other words, I only want 4 bits. And then my command, I take that and I OR it with LCDE. I then select registers using this little bit of code. Again, I take my command and I OR it with not LCDRS. I write out my byte. I toggle the E pin by saying it's ANDed with not whatever's there. I then write out that command again. Then I write the low nibble. So I say my command is this byte that was passed in, and I'm not shifting it this time, and I AND it with 0F hex, and then I OR that with LCDE. And I select the registers again, I write it out, I toggle the E pin the exact same way. I have a small delay in here just to keep things a little bit sane, and that's that. My data function that writes out data does the exact same thing, except here I'm going to select DDRAM. So notice the only difference between these is here I had a tilde, a not this, whereas here I'm going to use an OR. I'm going to OR it with LCDE. All right. And then I toggle the pin as before. So then I have another convenience function that will write out a string, and it just calls write data repeatedly until I get to a null. It's just a little loop. I have an initializing method that clears the screen, send it a reset command, tell it what function set to use. All of these things I've copied generously from some Arduino code. Here's a command to clear the screen, and then I wrote some helper functions that would write to the top line and to the bottom line. So I send a command that says put the cursor here, basically, and this writes to the top line, this writes to the bottom line. So notice the only difference is this part right here. That's the top line, and this is the bottom line. Okay, so if you look at the code for the main application, all I've done is wherever I'm doing status outputs into my device, I'm flashing LEDs here. You will also see strings being put out. So here it says insert your target. So first it comes up and says USB duplicator, insert original. Then it tells you to insert the target. And once it gets going, if there's an error, it'll tell you what the error was. And then eventually, after everything is enumerated, you get to the main loop and it just says, I'm copying. Which is convenient, but remember that it still has the LEDs. So the LEDs will still strobe. So you will see both a copying on a message on the LCD screen, and you will see the LEDs flashing. And then when it's done, it tells you All done. So there you have it. You don't really have to change much to your code, but you can make your device a lot more user-friendly. That's all for this video. See you next time. And remember, if you're enjoying these videos, tell a friend, help us spread the word about Pentester Academy. Thanks a lot. Hello, everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to talk a little bit about USB write blocking. In particular, we're going to focus on write blocking through software. In a future video, we are going to discuss making your own hardware-based write blocker. As some of you may have already guessed, we will use the same FTDI microcontroller chip, the Winkel M2, which we used for our duplicator in a previous video. So let's start with Windows. On a Windows system, I can write block USB mass storage devices. Now, one issue with doing this is that it's an all or nothing thing. I can block all USB devices or none of them. So if you're a system administrator and you're trying to block exfiltration of data, this could be a good option for you. If you're a forensics investigator, however, this might not be what you want. As a forensics investigator, you might rather block some devices and then allow the use of other devices for storing images from the subject devices. So might not be what you want, but how do you do this if this is something that you want to do? Well, all you have to do is set a registry key. What is the registry key? The registry key is under H key, local machine, system, current control set, control, storage device policies, write protect. So if you create this key and give it a value of 1, you will turn on this behavior. Incidentally, if you're not working on a live Windows system, you're working on a dead Windows system, you have an image of the file system and you want to make some changes to the registry for that Windows system, you can do this using a registry editor. In that case, instead of current control set, you would likely want to substitute control set 001. All right, so that's Windows. What about Linux? Is write blocking better in Linux? Well, of course it is, because everything is better in Linux. We already knew that. So in Linux, if I want to do some write blocking, I can use something called udev rules. Some of you may be unfamiliar with udev rules, but udev rules allow you to determine how all your devices are handled when they're connected, disconnected, etc. So you can set up a bunch of rules that allow you to have, a device that is given a particular name, a device that is given a particular device number. You can set up permissions for how that device is mounted. There are all kinds of powerful things that you can do with udev rules. It's actually way beyond the scope of our course here to dive into these in depth, but in the next video we will show you a demo of how you can do this with Linux. And here's the idea of what we're going to do. We're going to take a special hub, what I call a magic hub. So you find a USB hub and figure out what is its vendor ID and product ID, and everything that gets connected to that hub, every block device, is automatically mounted and automatically mounted as read-only. So what's a block device anyway? In Linux, we have two basic kinds of devices. We have block devices and character devices. And the only difference is that block devices deal with chunks of data and character devices deal with bytes of data, essentially streams of data. Many devices, by the way, are mounted as both. And this method is suitable for hard disks and anything that you can mount via USB. So this has a nice ability. You can mount stuff, you can get some nice speeds when you mount things, and all of that. All right. Now, what we'll find in the next video is because of the way USB devices that is, are handled in Linux, you're going to need multiple UDEV rules. The reason for this primarily is because the UDEV rules are processed at different levels. So if you have a device that's connected, at first there's some preliminary device identification that is done, and at each stage you don't have all of the data that you need. So when there's one rule being run, that rule doesn't have all the data. So in order to accomplish our write blocking, we will actually need a set of rules. And we'll see in the next video how this data gets passed back and forth. That's all for this video. As always, if you're enjoying these videos here at Pentester Academy, be sure to tell your friends. Hello everyone. Welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, as promised in the previous video, we're going to do a little demo of write blocking using Linux. So how does this work? I'm going to go ahead and bring up some UDEV rules. We talked about this in the previous video. We said that UDEV rules are Linux's way of handling new devices. So handling devices in general. So whenever you have a new device that's connected, you want to determine what it gets named, how it's attached, who has permissions, all those other things. UDEV rules determine that. So when you have a custom UDEV rule, you can put it in a certain directory, and this file 10-protected mount-rules is such a file. Now, if you're familiar with startup files, you know that they're often named as a number followed by some meaningful text. And this is the same case for our UDEV rules. So the name determines the order in which these are run. So giving it a number of 10 determines when it should be ran. And my first rule says, if the action is an add, someone has added a device, and that device is part of the block device subsystem. Some of you are familiar with Linux devices, and you realize there are generally two kinds of devices. We have character devices that operate on streams or data at 1 byte chunks. And then we have block devices such as drives that operate in bigger chunks like sectors. Many devices can be both, but for our purposes, when you mount a hard drive or a thumb drive, it is treated as a block device. So if it's a block device that's been added, and if the kernel name for that device is SD, then something else, followed by a number, that tells you it's a drive of some sort, right? Because as you probably know, the first drive in your system is SDA, and the first partition on that drive is SDA1. If there's more than one partition, you'll have SDA2, etc. And if you add another drive, it will be SDB. So this says I am a block device and I'm some sort of drive that the kernel is trying to mount. This next condition says, am I a device that has a vendor ID of 1A40? That's the vendor ID I've set up for my system. You can set it up differently. In the next video, I'll actually show you the install script for this. Now, one thing that's important to note, in UDEV rules, you can use adder, and then there's adder S. The difference is adder means me, this device. Adder S means me or any parent devices or super devices, if you will. So in this case, it's not my thumb drive that's been plugged in that has this vendor ID. It's my Magic Hub that we talked about previously. Similarly, I'm using adder S for the product ID. If all of these conditions have been met, notice the double equal signs, then I will set an environment variable called fillMount equal to 1. I will set a second variable called fillDev equal to %K. So what is %K? %K means please substitute the kernel's name for this device. So it will be SDB1, SDB2, etc. And add something to the list of scripts to be ran. So here's a script that is going to be run when I add a device that's a block device that meets all of these criteria. And notice that I'm running prot mount, and I'm also giving it that kernel name. If I look at the remove, I will see something very similar. The only significant difference is the action is now remove, and the environment variable fill unmount is set to 1, and prot mount 3 is ran. Some other rules. Here, if fill mount is equal to 1, which means I try to load a block device downstream from my Magic Hub, then I will set udisk's presentation hide equal to 1. What this does is this eliminates that pop-up screen that's going to say, hey, there's a new media, would you like to load it? Also related to that, I set auto mount hint to never, and then I run a second script. So here I'm going to run prot mount, and then later I'm going to run prot mount 2. And we'll look at these scripts in just a bit. If fill mount is not equal to 1, then I say go ahead and unhide the presentation and always give a hint. Here, if I've set fill unmount to 1, I will run prot mount 4. Right, so let's have a look at some of these scripts. The first script, prot mount. All this script does, it calls bin bash, and then it echoes a new script to prot mount 2. Previously, we said that you don't have all of the information you need at one juncture, and that's why we have this kind of strange process where I have a script that makes another script. And if you look at the commands for the script, it's pretty basic. It creates a directory and it uses the passed in kernel device name, does a chmod to that directory, mounts it as read-only, no access time updates, and it chmods that script that was just created. And sure enough, if I look at my prot mount 2, the last time this was created on my system, it created SDC1. That was the device name for my thumb drive. And it was mounted as read-only. Again, if I look back at my rules, the first rule says, okay, you are mounted downline from my Magic Hub. Basically, you were plugged into my Magic Hub or something that was plugged into that hub. So you are going to get mounted as read-only. I'm going to run this script, which creates the second script, which is run here. Similarly, if I look at the remove process, I have prot mount 3, which creates prot mount 4, which will unmount and remove the directory. So once again, this is what prot mount 4 looks like. So when you look at it, it's actually quite simple. Now, again, why the multiple scripts? We have multiple scripts for the simple reason that when you initially plug in that hub, you don't know what's going on. You don't have a device that's downstream. And when you initially plug in the block device, it's recognized as a block device, but it's recognized before it actually does the mounting. And that is why we have to set an environment variable and then run a second script. That's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. See you next time. Hello everyone, welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to cover the install shell script that was used in the previous video. So in the previous video, we talked about using udev rules in order to create a magic hub. And this magic hub had the property that whenever you plugged it in and you plugged any device downstream from it, either directly plugged into it or plugged into a hub that's plugged into it, that device gets mounted automatically as read-only. So how can we easily do this? We saw the scripts that get generated, but let's look at how we install them. So if I look at my install script here, you'll see it's pretty basic. The first line is our special comment, the pound bang or hash bang or shebang, depending on who you ask, followed by the request to run bin bash. Then I unset two variables. I unset a variable that I'm going to use to store the vid and another one for the PID. Then I define some functions. Defining a function is actually fairly simple to do with shell scripts. This function is called usage. You define it using the keyword function, followed by a name, and then in curly brackets, you put your function. Now, here I'm saying echo usage, and my usage is sudo, and then notice it says $base name $0. In other words, that is my script. I want to run my script. I don't want to present the entire path. And this is another little tip for you. If you're not familiar with using the command line in Linux or shell scripting, if you put something, a command, inside parentheses that are preceded by a $, what this will do is actually execute whatever command this is and then pass the results to the next script. In here, I'm just saying you want to put --vid --pid. I have an example. And then here, I'm doing another little cool thing where I am printing out what follows until I reach this token, EOF. So it says, here's the usage, and then it prints out an empty line, and then it says, bugs email to me. Here are the required options, and all of this is print out until you get to the end of file. Now we have exit, which means, okay, if I've called usage, it's because somebody messed up. So please exit my script. And of course, the function ends with a curly bracket. Here's another function that I've created called create rule. Here, I use the same cat command, but instead of going to the screen, I'm actually going to send my stuff to a file. Which file? That 10 protected mount rules file that we discussed in the previous video. Which directory is it in? It's in etc udev rules.d, along with the other custom rules that you can create. And here I'm going until my marker of _EOF_. So why am I doing this? Here's why. I'm going to cat out all of these things, and here, if I have an environment variable called vid, it will be inserted automatically. Notice the $ and then the curly brackets. By the way, you can get away with just using $vid, but it's considered bad practice because it's kind of dangerous. You could have some collisions if you had something that started with vid, and weird things could happen. Like maybe you have something called VI that's defined. So you have to be careful about that, because then you would get what was defined in VI followed by the letter D. So it's always safest to put your environment variable names inside curly brackets, as has been done here. The exact same thing is done with the PID here. Once again, this is done in the follow-on rules. Right, so all of this is put out to this file until you get to the end of file marker. I define another simple function called copy scripts, and it says if not -d, if this directory does not exist, etc udev scripts, then make it. So this is a simple conditional statement for shell scripting, and it ends with phi. It's another funny thing about shell scripts. If you have something that starts one way, you typically spell it in reverse to end it. Then whether or not I've just created this directory, I'm going to copy all of my prot mount scripts to that directory. So those are all functions. I haven't actually started running anything yet until I get here. Now when I get here, I'm going to parse my command line, and it's going to say while not 0 or not null, $1, do this. So look at that variable, that command line variable in, and if it is -h or --help, it calls usage, which remember at the end of that function it exited. I use the double semicolon to separate my choices. Here, if it's --vid, then I send my environment variable of vid equal to the next argument. Again, I end this case with 2 semicolons, and the same thing is done for PID. My case statement is closed with ESAC, or case spelled backwards. I then call this method called shift. What this does is it takes all of my command line arguments and shifts them to the left. So what used to be $2 is now $1. And this proceeds until I am through. When I'm through, there's no more arguments, and this will fail, and then it goes to done. Now, I just call create rule, now that vid and pid have been set, and I call copy scripts. That's it. Very simple script, and that's all you have. That's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. See you next time. Hello everyone. Welcome to USB Forensics and Pen Testing here at Pentesting Academy. We've made a lot of progress so far, and in this video we're going to move to the topic of hardware write blocking. In the previous videos we talked a little bit about software write blocking, and so now we're going to talk about doing the same thing but using hardware. So a high-level design of what we are going to do. As some of you may have expected, we're going to use the FTDI Vinculum 2 chip again, the same one we used for our duplicator that we made. We made the simple one and we made the slightly fancier one. And the way that this device will work is that the device itself will emulate a standard mass storage device, and it will connect to an actual device. So it's going to enumerate an actual USB mass storage drive, and to the PC that's connected to the other port, it's going to look like any old mass storage device. Now, all of the USB commands, those mass storage commands that we talked about in previous videos, will be inspected, and only whitelisted commands will be passed through. Now, you might say, why whitelisting? The biggest reason for using whitelisting instead of blacklisting is to future-proof the design. So for example, today you might have various write commands, write 6, write 10, write 12, write 16, whatever, right? So if tomorrow there's a new write 32 or write 27, who knows, some new command that could change a device, you don't want a device that would pass through that command. You would rather have a device that will block any commands that it doesn't consider to be safe. So that's how the device is going to work, and there will be handler functions for every possible command. So we're going to interpret the commands as they come through, and then we're going to say, okay, for this command, call this handler function. And this will make more sense when we get into the actual details of the device. Now, a few important notes before we get started. As we've talked about before, some devices don't work very well at full speed. The standard requires that these devices operate at full speed, but it's like the aircraft engine that has to operate at half of its maximum oil capacity, but not very well. There's already a disadvantage of using full speed because you have smaller packets and there's more overhead for each packet, and of course it's slower. But when you add to that the fact that many of these devices are not optimized for operating at full speed, it can get extremely slow. So that's something you need to know. Also, you need to know that Linux loads more information initially than Windows. So what you'll notice if you use this device and you plug it in to a Linux system, there will be a longer delay before the device comes up than what you'll find for Windows. How long of a delay? It really depends on the speed of your device and the size of the device. If it's a large device, it might take a minute. So just be warned that that might be the case. Other things you should know. The 64-bit Windows systems seem to have some issues with this device, and it seems to be related to the fact that they really do not like to talk at full speed to any of these devices, even though they're supposed to support that. Now, these issues, I'm hoping, will be addressed when FTDI releases this new chipset that has been coming out any day for a while now. They had claimed to have shipped by the end of 2014. It's now 2015, and they haven't come out just yet, hopefully soon. But it's hoped that these new FT90X series chips will fix these issues. And why would I think that? Well, number one, they're more modern. They're brand new. They're not several years old. And number two, these devices are capable of high-speed USB, which should counteract a lot of the problems that you might experience. So you might question why do we bother with this? Well, it's still usable now for many people, and it's also a good learning experience. It is quite likely that when these new chips come out, you can take the existing code that we're going to discuss and with very small changes create a high-speed device. All right. So what's the device look like? Well, here is one of my devices. This is actually my prototype, and this is based on a FTDI, the development platform with one port. Right? We don't want the two-port version because we want one of these to be a host and one of them to be a slave. So if you look, you will see that I have some wires that have been soldered on here, and all I did was I took a USB cable and cut the end off and soldered on these 4 wires. And you can't see it because it's covered with hot glue, but there actually are labels on this board. And if you're wondering about this red wire was just a little goof up that I had. I unsoldered these header pins off of this 32-pin development board, and I should have just clipped them. So that's a little tip for you if you're recreating this device. When I unsoldered them, one of the pins, the pad on the board came off and it was the ground. And so I had to run this little jumper to another ground in order to get everything to work. And that's why it looks a bit funny. All right, well, that's all for this video. As always, if you're enjoying these videos, please tell a friend. We would love to deliver even more exciting videos to you. And you know how it works. More subscribers equals more videos. See you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pen Tester Academy. In this video, we're going to continue our discussion of hardware write blocking. And we're going to start to look at our code for our hardware write blocker. And this time out, we're going to look at threads and helper functions. So let's start with application threads. We have two application threads. One of them enumerates that USB mass storage device, the actual device that you've plugged in. And the second one presents a fake mass storage device to the PC. Now recall from the last video, we said that save commands from the PC are passed on to the actual USB mass storage device, and unsave commands are blocked. And we'll see some more details later. It turns out that some of them aren't necessarily blocked, they're just return success when they didn't do anything. We'll talk about why that is. We, of course, use semaphores to coordinate these multiple threads. So that's it. There's the two threads. One of them talks to the actual device and the other one talks to the PC. And we use things like semaphores to coordinate these two threads. We also have some helper functions. So we have a helper function that opens the devices, and we have another one that attaches the mass storage devices, etc. One that closes the devices, and then one that checks the mass storage device status. So let's go ahead and let's have a look into the code. So where's the code for all of this? Well, it's here. So here I have my Windows virtual machine, and here's my main method. And most of this is boilerplate, stuff that's created automatically for you. And you'll see here's two prototypes for my threads. One of them is called handle CBW, handle command block wrapper, and the other one says host enum. Right. I have handles for my different devices defined. I've defined my block size as 512, which is the most common by far block size. And I'm going to say that the maximum number of LUNs, logical units, or partitions is 1. And I've defined my main method. In my main method, I'm going to initialize stuff. Again, all of this is set up for me automatically. Devices are created. I initialize my USB host, and I tell it I have 4 interfaces, 8 endpoints, and I'm going to be transferring on 4 of those. And here, I create my 2 threads. I create the first thread, I give it a priority of 27, and it's going to get a K of RAM for its stack, and it's going to call handle CBW, and here we have a name for it. I do something very similar here. It has a priority of 28. the same amount of RAM, and it will enumerate my host. Once those have been created, I call start scheduler, which has it off and running. All right, so what are some of these helper functions? Here's one that gets the connect state for my USB host. So it takes a handle to USB device and it asks, what's the state? So it starts out saying, well, it's disconnected until I know otherwise. If this handle is legit, then I'm going to execute the command, and the command is USB host get connect state. And again, I create a structure and then I pass in different parameters. So here's my structure, USB host IO control command block type. And I send that command. It returns my connection state into connect state, and that's what I return. So pretty simple. Another helper method that opens my drivers. It's going to open a driver for port E. Port E is used for write blocking. If I use the vinculum or Vinco board, which I've not used here, I need this port. So for the most part, you can ignore that. And I can also use some ports for things such as LEDs and such. But the main thing is I want to power up my host and slave bulk only mass storage device ports. So that's my little helper function for that. And then I have another little helper function that attaches the drivers. So here I'm going to attach to each of those drives, each of those devices. And then I have another helper that closes those drivers when it's all done. That just makes my life a little bit simpler. All right. So that's all for this video. As always, if you're enjoying these videos, tell a friend. In the next video, we're going to talk a little bit about other parts of this application. See you then. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pen Tester Academy. In this video, we're going to continue the discussion of our hardware-based write blocker. In particular, we're going to look at host enumeration and how that's done for this device. So once you've enumerated your actual mass storage device, your actual thumb drive, a variable is set in the other thread in order for it to know that you're ready. And also a semaphore is signaled. Again, semaphore, if you signal a semaphore, you can have another process that's waiting for that semaphore, and as soon as somebody signals it, off it will go. Now, this thread mostly sleeps and occasionally checks for a connect or a disconnect of the USB mass storage device. And the reason that it mostly sleeps is a lot of what's going on with this blocker is actually handled by the other thread and all those handler functions that we'll talk about in the next video. So let's go ahead and we'll have a look at the host enumeration code. So let me go ahead and pull up my virtual box. This is where we last left it. And here, we were just getting ready to start into this host enum function, which is run in its own thread. So how does this work? Well, we define a couple of variables, and once again, some of these things might look a little strange to you if you're used to doing PC programming. Remember that we're talking about a very small device that doesn't have a lot of RAM, and so you will see a lot of reuse of variables, and you will see a lot of variables declared on the stack, as opposed to using something like malloc. And why do we do that? Because allocating memory on the heap is very expensive in these little devices. So I set up a couple of different variables here. I have a buffer that's going to hold the command block and some other devices as well. I have a series of structures that I set up, such as this IO control block structure that's used for the bulk only mass storage device, some handles, some generic IO control structures for USB host, and I also have some structures for attaching those devices, that USB mass storage host device. I open the drivers using the helper function that we went over in the last video. I attach the drivers, and then I sit and I wait. I have a do loop, and I check, and I say, is this bus available? And how do I do that? I call USB host connect state, which is another helper function I defined in the last video. And I say, is the port state enumerated? In other words, is this guy completely ready to go? If it is, then let me find an interface that says it's mass storage and it's SCSI and its protocol is bulk only mass storage. I get ready to call this device find handle. So I'm going to make this call, and I'm going to find the handle by the class. Once I do make that call, I'm going to check and say, all right, did this work? If it failed, you'll notice that at this moment, if it failed, I don't really do anything differently. Just because all I'm going to do is try again. Okay, and then we try to attach to our device. It's enumerated, it's the right kind of device. Please attach the bulk only mass storage device driver to it. And we call this command. We're loading an IO control structure with this command code. Please attach. We make the call. If this succeeded, then we're going to set this variable flash connected equal to 1. That tells the other thread, yep, there is an actual device here. And why do we do this? Because if we didn't do this, the device could enumerate to the PC, right? My write blocker could tell the PC, I'm here, but there's nobody really listening. There's no actual mass storage device, and that's a problem. We also will signal the semaphore enummed, and once again, signaling that semaphore causes the other thread to start because it is waiting on the semaphore. We'll see that thread in the next video. And if this didn't succeed, then I say, nope, not connected. If we attached, or even if we didn't, every 2 seconds, I'm going to check. So I'm going to delay 2 seconds so I'm not burning up CPU cycles. And if it's enumerated, I'm going to check every 10 milliseconds for a new connection. Excuse me, if it's not, if I'm out here, and then I have my while 1. So this is an infinite loop, and it'll just keep on going, and it'll try to enumerate a device, and that's pretty much it. Well, that's all for this video. In the next video, we will go through the other thread, which has a little bit more code, and we're going to wrap this all up eventually with a nice big demo. So as always, if you're enjoying these videos here at Pentester Academy, please tell a friend. See you next time. Hello everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to continue our discussion of a USB write blocker. And in particular, we're going to look at the USB mass storage emulation code in our write blocker. So remember that we have a thread in the code that is going to connect to the device. And then we have another thread that is going to emulate a device to our actual PC that we've connected. So what does this thread do? It interprets those command block wrappers, right? So the command blocks inside, and it will call an appropriate handler for all of the different cases. So it first decodes the command, and then it calls a handler. And it will make use of a couple of helper functions. And those helper functions include one that will forward a command block wrapper to the actual device, one that will send or receive data from the device, and one that will return a command status wrapper. All right, enough talking. Let's look at some code. So let's look at a little bit of the code. Now here, you see we have one of those helper functions, forward command block wrapper to device. And it takes a handle to a command block wrapper, takes a pointer rather, and it will look at what's been written, and it calls write. It's pretty easy to understand. It just writes to the device, and it returns how much was written, which is set right here. Right? We give it the address of that variable, and then we return that variable. Here is our receive method, where we receive data from the device. All we do is we call read, and we return how much we read. Forward data to the slave, we write to that device, the slave device, which is the device that's pretending to be a mass storage device. And here we receive command status wrapper from a device, and we forward it to the slave. We know the length is going to be the same. And then we have a whole bunch of handler functions, right? And here is just one example that handles an inquiry. Creates a buffer, 64 bytes. Creates a little structure, command status wrapper. What does it do? This is a safe command. So since it's a safe command, it forwards this command to the device. So it takes the CBW, forwards it to the actual device. And then it gets a response. Once it gets the data from the device, it forwards that to the slave. Then it will receive a command status wrapper from the device, and it forwards that to the slave. So in other words, real quickly, it will first say this is safe, send the command to my actual drive, get data from my actual drive, forward that data to the slave, which ultimately goes to the PC, and then receive a command status wrapper from the device and forward that on to the slave, which again ultimately goes to the PC. So if you look, you will see a whole set of these handler functions in the code. Now remember that there are three possible phases: command block wrapper, possibly data, if there's data to exchange, and then command status wrapper. So each of these has at least two. So here I say test unit ready. This is a command that sends an awful lot. It's forwarded to the device, and then it just receives a command status wrapper. There's no data transport phase in this case. And then it forwards that to the slave and then ultimately to the PC. All right, read. Read is a safe command. Here, I won't go into all the details, but we have a logical block address and some other parameters that are set. And then you'll see this case statement. The case statement is because there are multiple read methods that are supported. There's read 6, read 10, read 12. All right. You have to support read 10. You probably support 6 and 12, but you're not required. Okay. All that changes is notice that with the 6, I have smaller LBA, smaller logical block address possible sizes, and here I have larger sizes that are available. And I have larger still with read 12. And here's a little bit of code that will do the read, and it forwards that to the device, and then it does the data transfer. It creates a block of memory, a little buffer. It reads, and then it writes. That's all it does. It reads from the device and writes it to the slave until it's done. Once it's done, it frees the buffer, and then it looks for a command status wrapper from the device, and it forwards that on. Read capacity is another safe command. Here it's just interpreted. Reporting LUNs. Request sense, again, is a safe command. So we'll scroll down here a little bit, and we'll try to find a command that is not a safe command and see what happens. Now, you might think that I can just return, there's a command that says illegal request. This command is not supported. You can send a not supported to a slave, which ultimately goes to the PC. And what I found is that Windows is pretty stupid. So Windows, if you say write is not supported by this device, it just keeps trying and trying and trying. It will repeatedly try to write to a device, even though you told it, I don't support writing. So what I've had to do is to make a change And what I've done is told it, yes, it all worked. So I actually receive all of your data. So I'll receive the data, but I don't actually pass it on. So you'll see here, I'm processing data, but not actually sending it anywhere. So if we scroll down, we will see some other handlers. There's an awful lot of them. Prevent, allow, removal that says, no, you can't remove that device, right? So again, if you look into the code, which is available here on SecurityTube Pentester Academy, that is, then you should be able to see more what I'm talking about. I realize it's a little bit hard in a video like this where I'm just sort of scrolling through code. Okay, here is the main function in this thread. It's called handle CBW. It waits for that semaphore that we talked about. And as soon as that semaphore says, I'm done, it stops blocking and it immediately signals it again, which might seem strange. There's a reason that you do that. By signaling it again, that way if someone disconnects, you can restart the device. Okay, so we have an infinite loop, and we say, do we have a slave BOMS context? If we do, I'm going to first build a CBW, and then I am going to read the CBW. I zeroed it out. I'm going to read it, and I have a big switch statement here. I say, is it an inquiry? I call handle inquiry. Is it mode select? I call mode select. Is it mode sense? I call that. So you can see there's not much to this actual thread. I'm mostly just calling various handlers. And again, you might look at this and say, well, this is kind of messy. It's messy like this because of the limitations of the microcontroller. You don't want to be calling a whole bunch of methods if you can avoid it. And there are some other things as well that you try to avoid with these small devices. So here I just keep in my loop. And if it wasn't all okay, I wait a second and I try and I check again. If it ever exits, I free my buffer. And that's it. That's really all there is to it. And again, it'll make more sense when you download the code and have a look at it. Well, that's all for this video. As always, if you're enjoying these videos, please tell a friend. See you next time.
Hi everyone, welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, I'm going to give you a quick demo of the USB write blocking device that we discussed in previous videos. The first thing you're going to need to do is you need to make a cable to connect to your device. So simply take an old USB cable, cut off the end that would have gone to your printer or other such device if you're using one of those old full-size cables, and you will find 4 wires. There will be a black wire, which is a ground, a red wire, which is plus 5 volts, and then 2 wires for the data. A green wire that is the data plus wire, and a white wire that is the data minus wire. Now, a couple of things about this wire. Most likely, the cable will be stranded wire. So what you want to do is take the wires and twist them together and then solder them. So you want to tin them with solder. Just put some solder on the tip of your iron and rub it over the ends. And what that will do is keep those ends together so that when you go to plug them in a breadboard, such as I have here, they don't come apart. The other thing you need to know is that the green and white wires are probably very thin because they only transmit data. If you're going to use a breadboard, I recommend that you have some 18 gauge solid wire, which is perfect for jumpers and things on your breadboard. Take that wire and solder it to the green and the white wires. Now, if you look closely here, I have the 64-pin version of the board with one port, which is why it says V2 DIP164. And if you look, you can just see that the red wire is connected to the 5-volt pin and that the black wire is connected to the ground pin. You can also see that the green and white wire are connected to U1P and U1M for positive and minus respectively. Once you have that wired up, now you need to program the board. So how are you going to do that? Well, you're going to use one of those debug boards that we talked about previously, and you can see that I have mine connected right here, and then load up the IDE and program away. Once you have the project loaded up, go ahead and plug in your debug board. And as a reminder, we talked about this in previous videos. If you're running this in a virtual machine, you might have to go to Devices, USB Devices, and make sure that the box next to FTDI V2 debugger module is checked. Otherwise, it won't detect this correctly and allow you to program. Take the source code that you've downloaded from our previous videos, or perhaps something you customized yourself. If you click on the Debug tab, you can go ahead and click on Flash. Once you do so, you should see some flashing lights on your debugger module if it's connected. If it's not connected, as is the case here, simply check or click on the check mark and bring it up. You might have to hit refresh, select, connect, OK, and now we're ready to flash. So off we go. First it's going to erase, and then it's going to program. You should get some flashing lights, as I see here on my debugger module. You'll notice that the right light is on constantly. I'm already at 75%, and I should be done very soon. Now that my device is programmed, I'm going to unplug my debugger and insert a flash drive and then plug in my device, like so. And what I should notice is that there will be some flashing lights here at my device. And if I have a look here at my computer screen, I can run a D message, and I should see that a SCSI device was attached. as it says here on my screen. And if I look over at my files application, I see that a new volume was installed. I'm going to double click on it, and you'll notice that I have flashing lights over here on my drive connected to my device. Now remember, previously we said that Linux systems load a lot more information up front than Windows systems, so it might take a minute or so for your device to appear, depending on how large it is. I actually have it up here now, so I can just go ahead and I can click through this, and everything works as expected. I can look in different directories, I can pull up files, I can try to edit files. So I have a little test text file here. I'll just go ahead and pull it up real quick. And all it says is hello world a couple of times. It's from another little program I wrote to do some USB stuff. So here I'll just add some random junk to the end of my file, and now I'll hit Control S in order to save it, and sure enough it says unexpected error writing to this device because the device is write protected. I can hit cancel, I can close this, close it without saving of course, and I can verify that in fact my device is still working properly. I click on directories, I see flashing lights from my device, and everything works as expected. So if I look at my boot directory, for example, I can pull up my grub file and notice that everything is as it should be. So that is the write blocker. Now in future videos we will expand on this device and we will show you how to make an impersonator device. So we'll make a device that can impersonate other mass storage devices and then show you how you can use that for some pen testing. That's all for this video. As always, if you're enjoying these videos here at Pentesting Academy, please tell your friends and help us make even more awesome videos for you. See you next time.
Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pen Tester Academy. In this video, we're going to take a look at USB mass storage impersonation. So the first question you might ask is, why would you want to do such a thing? And there are a couple of reasons. A lot of companies have started to use endpoint security software. And the software that they're using allows them to restrict what kind of portable or removable media can be attached to their networks. So, this makes sense from a security perspective why you might want to do this. Essentially, what some of this software does is the USB equivalent of MAC filtering. And as all of us know, MAC filtering is not terribly effective. Just as MAC filtering is not effective, neither is filtering based on vendor ID and product ID. So the device that we're going to describe over the next few videos allows you to go into an organization where this is practiced, take your device, mount it. Normally that wouldn't be the case, but you can mount it and inject some sort of a payload into their system, and you can also exfiltrate data. So here is a look at the device which I built. This device I actually presented at DEF CON 20, I believe, a few years back. And what is this device? Well, it's based on the right blocker that we created before. And not terribly surprisingly, you see here we have our Vinculum 2 development board. In this case, it's using the 32-pin option. And this, of course, is just the debug board. So you don't normally need this when you're running it. And I have a thumb drive attached. And now we have something new. We discussed LCD screens such as this one before. We talked about how that interface looks. And the new thing is buttons. So now we're going to add some buttons to our device. So how does this device work? Operationally, it works like this. You take your thumb drive that you want to have mounted. You insert it in this device. Then you plug it in to your target computer and it'll boot up. And here's a welcome message. Once the welcome message has been displayed, it will allow you to either give it a vid-pid combination or to attempt automatic mode. So automatic mode works like this. In auto mode, it will try a vid-pid combination. If it's unsuccessful, it'll go to the next one. More about that in the next slide. The other thing that's different is that this has write blocking just as the write blocker does, but this has a toggle switch that allows you to turn that on and off so that you can block it initially in case something like antivirus might try to delete your stuff. Once you've killed the antivirus, you can toggle it off in order to exfiltrate data. So, as we said, it builds on our write blocker design, and it does have the ability to toggle that feature. The vid-pid, either you can select it with two of the buttons. After a delay, if you haven't selected a vid-pid combination, it will start trying, and it uses a list of the 500 most common combinations. And essentially what it does, if you start talking to it and then you stop, it assumes that you're blocking it. And then it goes to the next vid-pid combination. You could also drop it to do an brute force attack. That's not the way I implemented it, but you certainly could do that. There are a couple of threads. There is a host and slave thread for the drive and talking to the PC. And there's something new. There's a new timer thread, and the timer will go into more detail in the future videos. Allows you to give it some time, and if it doesn't succeed, then it goes to the next one. Also, there's another thread for handling the buttons. And in terms of the details, here are the wiring details. So you have this slide. I'm not going to go into all the details, but essentially the buttons are connected to these pins, 12, 14, and 15. If you're using the V2DIP1-32 module, and the LCD is connected to the pins shown. You have the two LEDs that indicate the write blocking status, and you might want to throw in a 220 ohm limiting resistor in order to prevent that from drawing too much current. And then we have our 10K potentiometer for our contrast control, which is the same as what we used in the duplicator. Now, there is an option to use the Vinco board that we described previously instead. Personally, I do not recommend the Vinco board. Some people have tried it, some people have had difficulty because the Vinco board has a couple of lines that have to be set up correctly in order to power the host port. And I've had some difficulty with timing issues when using the Vinco. So unless you really want to try that way, I would recommend just stick with the development board. Well, that's all for this video. As always, if you're enjoying these videos, please tell a friend, and I will see you soon. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pen Tester Academy. In this video, we're going to talk a little bit more about our impersonator, and in particular, we're going to look at buttons and timers. So, buttons. They sound very simple. When it comes to doing digital electronics, you have two options with buttons. You can either have a push button that is active high or active low. So what does that mean? We'll start with active high. So this picture here on the right shows a button that is active high. What that means, if you connect the high voltage, then the button, and then the pin for your microcontroller, in our case, the Vinculum 2, when you push the button, you get 5 volts on the pin. Simple enough. Now, normally, we will install a resistor, such as this one shown here, between the button and ground. And why do we do that? We do that because we don't want a lot of current flowing. We're not trying to drive anything, we're just trying to flip a switch. We're trying to say the voltage went high. So that's one option. The other option is active low. And it looks very similar. The only difference is now the switch is on the other side of the pin, if you will. So here we have our plus 5 volts, and then we have our resistor, and it's connected to our pin. Now, why do we have this resistor? The same reason. We don't want to constantly supply a large amount of current. We just want to have 5 volts on the pin. When you push the button, you're shorting this to ground, and then you really don't want a lot of current flowing. How does this look? Something that's looking like this. So here's a close-up of the push buttons for my impersonator. And you'll notice there are 3 wires here that lead to the Vinculum 2 development board. And those are on one side, and on the other side you can kind of see that there are 3 wires that are tying these buttons together. One thing you can't see is that underneath this LCD display you will find those limiting resistors. Again, to limit the current so that not a lot of current is flowing when the button is pressed or not pressed. So what does the code for this look like? It's really pretty simple. You read the port. In my case, I used port E. You get the bits, the bit mask for the buttons. And while somebody pushed a button, you check and you say, did someone push the right button? So what you have to do is you have to determine which bit applies to each button. So if you look at this guy here, when it says F7, F7 means everything but the bit representing 8 is off or on, depending on how you look at it. So this would be for that bit in the port. And we'll see what that means here in a little bit. Now let's talk about timers. Timers are something that most microcontrollers and many CPUs support. They can count up or down. They can be a one-time or something we call a single shot, or they could be continuous. They just continually run over and over. Now you can block until a timer expires, and we start and stop a timer in our application. So we start it, and if the device successfully enumerates, we stop it. So it's very simple how this works. If the timer expires, then we say, oh, it must not have worked out, and we go to the next vid-pid combination. Great, so let's have a look at some of the code that we need for this. So here we have our code. We have some of the code that you might recognize from before that does the LEDs and the LCDs. And then we get into our timer. So our timer thread, first it creates a structure for talking to the timers, and then it opens the timer, and there are a couple of timers available. So we're going to use timer 0. We set the tick size to be in milliseconds. Microseconds are another option here. Then we tell it we want it to count to 1,000 or 1 second. We tell it please count down. We set it to a one-time timer, a single shot timer here. And then we enter this loop where we tell it, okay, let's start our timer. We'll wait until it's complete. And if we get here, if we got to this point, it's only because that expired. And that's pretty much it. So there's another thread that we'll see later that affects these timers. So there's another thread that actually stops the timer. So this thread will sit in block waiting for that timer to expire, and it never does because somebody else paused it. And that's basically the idea. All right, so if we go to the code for our buttons, you'll see that it's pretty simple. We read the port. Again, it's port E that we use. And then we say, was it this button, the write protect button? Again, this one, F7, means it's the bit associated with the value 8. And in this case, because turning the write protect off is pretty serious, we actually delay a second and we check again. This is a very primitive form of something we call debouncing. A mechanical switch like this often will vibrate on and off as you push it or release it. And this is the absolute simplest way of detecting that, not necessarily detecting that, but dealing with that. And if the button was pressed, then we toggle the right protect. And then here we have FB. Again, that tells us which bit is associated with this button. If you pushed the plus button, it will add to the index and it will update the current value of the vid and PID. Similarly, if you press the down button, the minus button, it will decrement from that index and reset the vid PID. It also displays this on the LCD screen. So there you have it. That's all you ever needed to know about timers and buttons. That's all for this video. As always, if you're enjoying these videos, please tell a friend. See you next time.
Hello everyone. Welcome to USB Forensics and Pen Testing here at Pen Tester Academy. In this video, we're going to do a quick demo of the USB impersonation device that we developed over the last couple of videos. Now I'm going to attach my device to my Linux system, and on this Linux system I have used UDEV rules to allow mounting from a particular vid-PID combination. So I'm going to go ahead and plug in the device. So it's plugged in. I select 324BC08 as my authorized vid-PID combination. And I see that it has successfully read my device, and I should see some sort of flashing from my thumb drive.
Now, if I look at my PC, when I've plugged in my device, after a little bit of time, it should come up with a new device. So right now, I'm looking here, waiting for a new device to show up. I can also see, oh, there it is. All right. So I can go ahead and click on that. And as we said before, it'll take just a little bit of time for this to come up, mostly because it's a full speed device. If I go to my terminal here and do an ls USB, I will see that yes, in fact, as we expected, I have mounted the device with the vid-PID combination of 0324 BC08. So I've successfully impersonated a different device. Now, here's another interesting thing that I found. I actually do not provide a proper string for the descriptors. So if you load this under Windows, it will tell you this is a PNY device, just as the right blocker shows up as a PNY device. In that case, using the correct vid-PID from an actual device. In this case, I'm actually faking it, and Linux is smart enough to actually look it up and say, no, that's not a PNY device, vendor ID. So I did think that was kind of interesting. So if I go back here, once again, here are my files. I can bring up various things. In fact, here's a presentation that I gave at Black Hat a few years ago on that right blocker. And it was an aptly named presentation that was called Preventing Oh Shit Moments for 20 Euros or Less. So there you have it. Everything works as we would expect. I can bring up some source code for the right blocker, etc. And once again, if I try to change something, it's not going to save. All right, well, I hope you've enjoyed this series and our talks about the impersonator. Before we go, I wanted to point out one thing really quickly, and that is that you could, if you know an authorized vid-PID combination, you could actually modify the right blocker directly, and that might be a little bit easier for you to do. So how could you do that? If you look at the code for the right blocker, and in particular, if you look at the slave file, you will see there are a bunch of device descriptors and other kinds of descriptors. And right here, you will see here's the vendor ID for PNY, and here is the product ID for that same device. So you can fake it, again, if you know the correct device and you don't want to build, the bigger impersonator that has a screen and buttons and all that extra complication, you could certainly do this with just the garden variety right blocker. And you could also put a single switch with a couple LEDs to toggle on and off the right blocking if you so chose. Well, that's all for this video. As always, if you're enjoying these videos, please tell your friends and encourage them to subscribe. Hello, everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to talk a little bit about dealing with Windows-only devices. So, what sort of things are we talking about? Well, I think a perfect example of a Windows-only device is this little guy. This is a SanDisk Cruiser profile, and as you can see from the picture on the left, this is a thumb drive, and what you see from the picture over here on the right is that this thumb drive actually comes apart and it has a fingerprint scanner. So this is a nice solution if you ever lose a thumb drive and you're worried that someone will steal your information. You can worry a little bit less if you have an encrypted drive such as this one. Unfortunately, the people at SanDisk decided, hey, let's make this only work for Windows. So that's a big boo for that. But perhaps we can do a little bit of reverse engineering and we can figure this out. So how would we do that? How would we reverse engineer this device? Because it only works under Windows. So here's a basic outline of the technique that we would use. First of all, we're going to have to run Windows inside of a virtual machine. And then what we'll do is we'll plug in the device onto our Linux box, and we will note the vid and PID, create a filter in VirtualBox that will allow this device to pass through into the Windows virtual machine. We have to make sure we run modprobe USB-mon in order to load that monitor interface for USB. Fire up Wireshark, insert the device with Windows running, and sniff and reverse and engineer away. So let's have a look at how this is in practice. When I insert the device, so I'm going to go ahead, I'm going to insert my device now. And if I do an ls USB, I see right here, this is a SanDisk Corp device, and here's the vid and PID. You might want to note those to make this easier, the stuff that you're looking to do. So I will go ahead and make a note of that. And now I'm going to have a look at VirtualBox. So if I look at VirtualBox and I have this virtual machine that I'm going to use, and if I go ahead and I click on Settings and then click on USB, you'll notice that I've enabled USB, USB 2, and I already have a couple of devices present. So I will go ahead and delete that filter, and I will click on the plus sign to add a new one. And here it will say, okay, I'm going to select from currently plugged in devices, and this is the one that I want. And now I can click OK. Going back to my terminal window for a second, I'm going to go ahead and load USBmon. So sudo mod probe USBmon. And now that's loaded. I can go back to my VirtualBox. I'm going to unplug my device, and I'm going to run up my virtual machine. And off it goes. While I'm waiting for that, I will go back to my terminal. So I'll go back to my terminal window here, and I'm going to go ahead and run Wireshark. So Wireshark is loading. Here it is. And I know from previous experience that I want to monitor USB Mon 3. Click on Start. And now I can go back to my Windows machine. Here, I'm going to plug in my device. I got the little noise, which I should get. And now it's asking me to swipe my finger. We'll see if this is successful. No, didn't like it. We'll try it again. This time it liked it. Great. So now, if I have a look, I should see that I've successfully loaded 2 drives. Now, one of them is a removable drive that has my information. So here I have some various documents on this. You also will have a hard disk that gets created for this particular device, and this has things such as this cruiser profile program that needs to get run. So I can go back now to my Wireshark program, and I'm probably safe to go ahead and stop this. Right. So from here, I can pretty easily go back and look at all the traffic and try to figure out exactly how this particular device works so that I could perhaps use it from Linux or Mac as well. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, tell a friend and encourage them to subscribe. See you next time. Hello, everyone, and welcome to USB Forensics and Pen Testing here at Pentester Academy. In this video, we're going to talk about something new. We've talked an awful lot about mass storage devices, and today we are going to talk a little bit about another common device called a human interface device, or HID. So what exactly is a HID anyway? Very common examples would be a keyboard, a mouse, a joystick, anything with a button really you can use as a HID. Another way you can think of a HID is it's anything that moves bytes back and forth. Possibly one way, possibly bidirectional, but most anything can be defined as a HID for interfacing with your computer. So how does it work anyway? Well, there are two basic protocols that you can use. Now there's this remedial mode, if you will, known as the boot protocol. And this is something that keyboards and mice support if they are usable when you first boot the machine. Because if you think about it, when you first boot the machine, you have a operating system that's not yet loaded. So, USB is kind of complicated. So you don't have something that can parse all these descriptors and do all these other things. You just want to get keys from the keyboard. And that's why there's this boot protocol mode of operation. Now, once USB is up and going, the operating system is running, most people would prefer to use the report mode. Now, when you're using the report mode, there are three basic kinds of reports. There are input reports, and input, of course, means input into the host. Output reports, which are optional, so you might want to write something back. For example, please turn on the caps lock LED. And feature reports, which can go either direction. So in terms of endpoints that are required, you have to have a control endpoint, which you should expect. Everything needs a control endpoint. And you also need an interrupt in endpoint. Now, to remind you, interrupt endpoints are meant for things that might occasionally send you data. So for example, a keyboard is not constantly sending you data. It only sends you data when someone hits a key. Optionally, you can have interrupt out endpoints. Again, this is an optional thing, so you might wonder, well, how does my keyboard light up the lights when I press caps lock, etc., if this is optional? And the reason for that is you can use the control endpoints if you do not have an interrupt out endpoint set up. So there's a protocol in place for that. Now HID has its own special descriptors. We talked about device configuration interface endpoint descriptors, string descriptors in the past. So HID defines its own class-specific descriptors, and these descriptors define various HID reports. And the boot protocol reports, again, are much simpler. They're fixed length, so they know what's coming. They know what's coming from the keyboard, what's coming from the mouse. And these are only defined for keyboards and mice. So why are we talking about this? The biggest reason that we're talking about HID at all is that a lot of people recently have done some work with developing attack devices that are hid devices. So for example, a keylogger might insert itself between the keyboard and the computer. Well, many of these things are implemented with microcontrollers, such as the Vinculum 2 that we've dealt with in this course. Most of these only support the boot protocol. So if you have a product that says, I can detect hardware keyloggers, it is probably looking for something like that. Oh, here's a device that only supports the boot protocol. That's not common for an actual keyboard or an actual mouse. Also, some of these devices have very well-known VIDs and PIDs. So that is another way you can detect them. Another way, if you try to transfer files, you say, I can't mount a mass storage device, but I have a HID, and that's the basis for some of these attacks. I want to look at this mass storage device, or this HID rather, and I want to exfiltrate data. So what people will try to do is they'll set up that out endpoint and they'll try to send a whole bunch of data. Normally that is for a couple of bytes here and there to toggle LEDs on and off and such. So those sorts of activities are also easily detected. Another way that these things are easily found out, if you have a composite device, not too many keyboards also include a mass storage device, for example. So that would also be a suspicious thing, especially if you have a keyboard that only supports the boot protocol and also has a built-in mass storage device. That is probably the most suspicious thing you would ever see. All right, so let's very quickly do a little demo. Well, first of all, I'm going to load up my USB mon. Going to run Wireshark. And here's my Wireshark. And I know from experience that this device I'm about to attach will be attached to USB Mon 3. So in my case, I have an actual keyboard. It's one of these little roll-up deals, but it's a legit keyboard. So I'm going to start my capture, and then I'm going to plug in my device. If I go back to my terminal, I will see when I do an ls USB, here's my device. Device 5 on bus 3 is my keyboard. So if I look at all of the traffic that's going to device 5, if I look for device 5, I should see just a couple of things going back and forth. We'll apply a filter. We'll just change this to 5. And now we see here is the start of my communications with this device. And as you might expect, we have the standard stuff. We ask for a device descriptor, then we ask for the configuration, and we do this twice. And the second time, we see that we have, in fact, gotten a descriptor and we look at it, and we'll see that it has two interfaces. The first one, Wireshark tells me this is boot interface. All right, that's only supporting that boot interface. And the second one is going to support a different interface. Well, that's all for this video. As always, if you're enjoying these videos, please tell a friend. We'll see you next time. Hello, everyone. Welcome to USB Forensics and Pen Testing here at Pen Tester Academy. In this video, we're going to have a look at hid descriptors and reports. So we briefly mentioned them in the previous video, and we're going to drill down just a little bit deeper, but not too deep in this video, just so you can kind of understand the sort of traffic you might expect. And again, we said that many of these attack devices that you might see only support the boot protocol. So if you wanted a device that's not so easily detected, you might have to consider supporting the full protocol for your keyboard, mouse, etc. So in these descriptors that define the hid reports, you have three different kinds of items. You have main items, global items, and then local items. So this will make more sense. We're going to look at an example pretty quickly here. But as you might expect, global items apply to everything, and local items only apply to the current section of that report, if you will. So what types of items can you have in this main category? Well, we have input, output, feature items. And again, these correspond to input, output, and feature reports, where feature reports can go both ways to and from the host, and input and output have obvious directions. And then we have a collection, an end collection item. So within those reports, we can have a collection of things that are sent. For example, if we have a mouse, we might want to send a collection of coordinates that describe its movement. Or if we have a device that can have multiple things pressed at once, we might want to send a collection of that as well. So all of these are defined in descriptors, so let's have a look at some of these descriptors. Here I have already loaded USB Mon, but if I hadn't, I could. And I'll go ahead and run Wireshark. As before, I will select USB Mon 3, start it, and plug in my device. All right, so I've plugged in my device. If I go back to my terminal window, I will see that I should have used an ampersand, but I didn't. So we'll just ls USB. And in this case, it's device 6, where this has been connected. Great. Now, one other thing I want to do, I'm going to go ahead and run gedit. And you might say, why are you going to do that? Well, I'm going to do this in order to generate some traffic on my new keyboard I just connected. So this is being typed on the new keyboard. And that's probably enough of that. We'll go back to Wireshark and we will stop our sniffing. We will apply a filter. And we said it's address 6 that we're interested in. So we can go to where this starts. And here we see the host has been connected. I get a descriptor request sent, a response, configuration first time, then the second request where I get the real deal. And once again, there are two interfaces. This is the only interface you might expect to get if I have a device that only does the boot protocol, i.e. your keylogger, your Teensy-based device that might be easily detected. And here I have another interface, and this one, notice that the class is the same. There's no subclass and no protocol. Whereas here, the subclass was 1 and the protocol was 1, which meant this is a keyboard and it supports the boot interface protocol. So a proper keyboard should support both of these. And I request some string descriptors. Nothing too surprising here. And I ask to set a configuration. So the configuration I asked to set here, I say, please set your configuration to configuration 1. I want to use the full protocol, is what that's saying to you. There's a response. There's a set idle request. Set idle request just affects how the device works when you're not pressing anything, and things like polling intervals. Don't really concern yourself with that. And then here we request a descriptor. And the descriptor type is 22 hex or 34 decimal. And here is the response. And notice the response that you get back is a HID report, because the HID report is, in fact, type 22 hex or 34. Okay, and we said there are different kinds of items. And here you can see there's some global items. There's always going to be a usage tag, and this says it's a generic desktop control. And here again, it's just saying this is a nice generic device. There's a collection of items here. Here we have some LEDs that are being defined. There's always going to be an application collection. And we can define minimums and maximums for different controls. So for example, we could say this is how many buttons we support, if it's a mouse, etc. So there are lots of things in here that you need to support. Now, this going deeper into this is way beyond the scope of our little course here. I could honestly probably do a class just as long on USB HID devices as the one that you're wrapping up here on USB mass storage devices. But I did think it was important for you to understand, just how complicated is it? This is a simple keyboard here. And look at all the things it has to support. And not supporting these is a big clue that, oh, you're probably not a legit keyboard. You're probably some other kind of device. So here, you set the report request. You say, this is how I would like to get my data. And you will see that there will be different inputs from your device to the host. And these different inputs are going to give you those keys that were pressed. Right? So you're going to get reports back from the device that tell you, okay, here's what keys were pressed.
This wraps up our discussion of USB hid devices. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend and help us spread the word. See you next time.
Hello, everyone. Welcome to USB forensics and pen testing here at Pen Tester Academy. It's been a long journey. We've covered a lot of interesting stuff. We've talked a lot about USB mass storage devices, how you could make forensic copies of them, how you could write block them, how you could impersonate them. And recently we talked a little bit about human interface devices and how those can be used as part of a pen test. And we also talked about how can I detect some of these devices that someone might use, some microcontroller based keyloggers or keyboards, etc. So I wanted to close out our course here by giving you a challenge. So this is the final challenge for this course. And my challenge to you is this. You will find a capture file attached to this video. In that capture file, I want you to identify all of the HIDs in the file. I won't say how many there are. And for each of those devices, determine what is the vid-PID combination, how many configurations does it support, how many interfaces does it have, and for each of those interfaces, what protocols do they support, and how many endpoints do they have. Now here's the real important thing. See if you can figure out, based on the traffic, whether or not this is a real HID, a real keyboard or mouse, etc., or if it is one of these fake HIDs that is used as an attack device of some sort, or a keylogger, etc. So that's it. That's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, tell a friend. I'll see you in the next video with the answers. Hello, everyone, and welcome to USB forensics and pen testing. In this last video, in this series, we are going to cover the solution to the challenge that we posed in the previous video. So hopefully you were able to identify the number of devices, number of HID devices in the previous video. You might have noticed some traffic from other devices on the same hub, on the same bus. So, that's the way it goes, right? We talked about this before. We said sometimes you just have to filter out everything. And here are the 3 devices that you should have found. So one of them is this keyboard, which is a legitimate keyboard. It's an actual keyboard. The second device you should have found was this guy. Now this guy is actually a PIC microcontroller board. PIC, if you're not familiar with them, they are made by Microchip. They're one of the largest chip manufacturers around, and PIC controllers are something just like the AVRs that you might be more familiar with in the Arduinos. Uh, Sometimes people think they're a little bit more hardcore. And then here we have our third device was a Teensy 3.1. And let's look at these in a little bit more detail. So in terms of the device numbers that were assigned when you looked at this capture, the keyboard was device 23, the microchip PIC 32 was device 24, and the Teensy was assigned an address of 25. So let's go ahead and walk through these solutions. So if I walk through my solutions here, what am I going to find? All right, so the first thing I want to do is look at the keyboard. So if I filter on address 23, I will see here it's asked to set its address, which it does, and the standard stuff. The device descriptor that's returned says, oh, I'm going to tell you later in terms of the class, etc. Then we have our requests. We say, please give me the configuration, and now really give it to me, all of it, second time. And the second time we notice that there are two interfaces. There's one configuration, two interfaces that are available. And as you might expect, the first interface is a boot interface. That's the protocol that it talks. So the subclass says I'm a boot protocol interface and I'm a keyboard. Also, it will tell you that I am having a second interface which has a subclass of 0 and a protocol of 0, which means please do the full deal. I'm capable of doing the entire protocol. Right. Now, if we zip back here real quick and we look at this response, we can get the vid and the PID. Here again, this is verified by Wireshark. Wireshark has a database of these things, and it says, oh, that's a Sigma Micro keyboard tracer Gamma Ivory. So that looks legit to me, and other ways that you can see that this is legit. If you trace further into the traffic, you'll see it returns the appropriate descriptors. It says, I'm a keyboard. Here's who made me. And when we look at the traffic going forward, we see that sure enough, it's accepting standard commands like set idle, and it's asking for a HID report. So here's the descriptor for our HID report. And as we talked about before, you see the global items, local items, and then you'll see a collection of main items. You'll see there's quite a few things in here. So this all looks good. This is what a proper keyboard looks like. If I look a little further down, I will see here's some of the traffic that's going back and forth. Another descriptor request. And there's some traffic coming in. So here I have some report traffic. You can also notice which endpoints it's coming in on, and that will give you some indication as well that this is in fact a legit keyboard. Other indicators as to whether or not it's legit, sometimes if you try to put too much information in too fast, that's another indicator that this is not a real keyboard. Great, so all of this looks pretty standard. So let's move on to device number 2, which was device 24. Now, if I look at this device, we start here. It set its address to 24, and it got a device descriptor. And the descriptor says, my vendor ID is Microchip Technology Inc. and my product is unknown. So that already is kind of a red flag. You might say, Microchip, they make microcontrollers, not keyboards so much. Again, some devices that you can build will allow you to override this, but a lot of them, it's not terribly easy to do so. Then we have a couple of other packets here. And we ask for the configuration first time, second time. And here on the second time, we see there is one interface. And what does that one interface look like? Sure enough, the one and only interface has 2 endpoints. And it is a boot interface. And it's a keyboard. So again, this is a big red flag to you. This says this is a bogus device. It only supports the wimpy boot protocol. It doesn't support the full deal, as a normal keyboard would. And you can look and see it's got an in endpoint and an out endpoint, which isn't a bad thing. But again, the fact that it has an out endpoint and it only supports the boot protocol could be a little bit suspicious. Again, someone could be using this to try to exfiltrate some data out of your computer. Naturally, if you look at the traffic that you're going to get from this guy, he supports US English, not surprising. Of course, the string hid keyboard demo, that's a big clue there. I should probably have changed that. And I might have been able to change a few other things as well. And here we see different traffics. There is one out packet that I saw back here. There it is. And again, this is probably sending out information about things like caps lock, etc. All right, so that is the second device, the microchip device. So let's look at the last device. The last device had address 25 assigned to it. And here we get the descriptor. And you have a very interesting vendor ID, Van Ogen Technische Informatica. And the product ID is Teensy Duino keyboard, mouse, joystick. So, this is a little bit suspicious. You have this bizarre vendor ID that corresponds with the manufacturer of the Teensy. So I'm a little bit suspicious. Let's see what else might make me suspicious. So we get our configuration first time, second time. So here I have my configuration. This configuration has 4 interfaces. Now, the reason that it has so many interfaces, for one thing, this is a keyboard, mouse, and joystick. So if I scroll down a little bit further, I will see that here is a boot interface for the keyboard, and note which interface this is. It's interface 0. And it has one endpoint. That one endpoint is endpoint 3, which is an interrupt endpoint. And then I see my next descriptor is another HID device. Basically, it's my keyboard with the full protocol. So that's a good thing. Unlike the pick example that we just went through, this actually has real live interfaces, that support the full protocol. All right, so that is supporting that on endpoint 5. And then here we have 2 more interfaces. We have keyboard, which we just talked about, and then we have a mouse and a joystick. So those are somewhat uninteresting. All right, so if we go forward with this traffic, let's see, we're getting descriptors that say things like, hey, I'm a teensy Duino. And we're getting our HID, so that's good. We'll get our descriptor. It's a very odd string descriptor, but that's what it is. We go through and we say, hey, can you give me that HID descriptor that shows me what the reports look like? And it does. And then we say, get me a report, please. And notice that there's some traffic here. And you'll see some traffic on some of the mouse and joystick endpoints, but not too much here. All right, so we have some data flowing in on endpoint number 3. And endpoint number 3 was, in fact, that first endpoint. So if you go back, so go back to the top real quick here and just make a note of the configuration when it defined the first interface. It said it has an endpoint, and that endpoint was number 3. So in terms of what's actually being used here, it's only using the very first interface. Now, that doesn't necessarily mean that this is bogus, right? But there are other ways that you could tell that, yes, this one is bogus. It's a little bit harder than the PIT controller. Now, one thing I should point out here we've used a teensy 3.1, right, which is considerably more powerful than the original teensy or even the teensy 2. Because it is much more powerful, it can emulate a proper keyboard. So how do you tell that this teensy is bogus? You have to look at other little clues, such as the vid PID combinations. You can look for mismatches. If you can say this is a known vid PID, or if they give you a bogus vid PID. If you look it up, so to speak, you can say, oh, you gave me this, but I know that that's not corresponding with the string descriptor that you also gave me. So those are ways that you can determine that this is in fact a bogus device. Other things like rates. What is the rate that you're providing keys to me? If you're providing keys to me at some insane rate and consistently doing that, I'm going to again be very suspicious that you're a bogus device. All right, so that is our solutions for our second challenge. I hope you've enjoyed this course. I know that I've enjoyed uh, developing this course and teaching this course for you guys. Uh, don't be afraid, however. This is not the end. There's new courses coming out every day on SecurityTube's Pen Tester Academy. So, you know, hopefully I will see you again in another course soon. And as always, if you're enjoying these courses, please tell a friend and help us spread the word and help us offer even more of these courses for you. See you guys around.